2001, and he has as a senior principal analyst of Malaysian Industry Government Group for High Technology in the Prime Minister Department since 2001. And of course, right now, Professor Dr. Harith Ahmad as a reviewer in IEEE Photonic Technology Letter in the United States of America, and of course, a fellow Academy of the Science from Malaysia. Ladies and gentlemen, no doubt again, please welcome Datuk Profesor Dr. Harith Ahmad. Assalamualaikum Datuk, selamat pagi dari Malaysia Indonesia.
Waalaikumsalam, selamat pagi. Give me one minute to set up my PowerPoint.
Yeah. Oh, you got a call? Yeah. Sembari kita menunggu, anytime, a whole time you're waiting, Mr. Harith Ahmad, it's with us again, and immediately, saya ingatkan kembali, we not bored to reminded you guys to click below on your chat room. Just check out your chat room, please. It's attendant. Maybe feel you to using your smartphone or your laptop or your PC to through that's a link and then click and join your name. Professor Harith, is that okay? Are you ready?
Give me about 1 minute to set the PowerPoint. Yeah.
Are you ready, sir? Share screen. Maybe our IT. Would you like to have Mr. Harith? Yeah, I believe that. Our IT is a very moving, faster respond. All right. Okay, are you ready? Yeah. I'm still not ready. All right, that's okay. Bapak dan Ibu, nanti diingatkan kembali, absen kita bikin 2 kali, pagi hari ini 1, nanti sore jam, oh, it's running through. All right, here we go. Ladies and gentlemen, it's time to Mr. Harith Ahmad. We're going to give you the 20 minutes for your presentation and a 5 minutes to answer any questions and any something like confusing from the participant. So, bagi Bapak dan Ibu yang ingin bertanya, if you have any question, just click below on the chat room. Just text on there, just write on there, and after that, after 20 minutes, Mr. Harith gonna be answered that question. We got a 30 minutes just only for Mr. Harith from Malaysia, and then it's gonna be cool. It's starting right now. Mr. Harith.
Okay. I hope you can see me. I hope you can hear me. You can hear me.
Yes, clearly.
You can see my slide.
Yes, of course.
Okay, thank you very much. Okay, sorry for 1 minute of trying to get the system up. So we are quite familiar with Google Meet somehow. All right. What I'm going to talk this morning, in fact, I would like to thank the organizer, the Dean of the Science Faculty of University of Padang, and also the Rector, Professor Negeri. Yeah? I hope I pronounced the name correctly for this morning, for me to be able to present. What I want to present for this morning is something that we have been doing for the last 2 years, where we integrate photonics with nanotechnology. It's a marriage between photonics. Photonics is nothing more than we are studying about light. We do work on light lasers, fiber lasers, and so on. And of late, last 2-3 years, we have integrated nanotechnology, 2D material, 2-dimensional material, into the photonic devices to generate short pulses. And my topic of my talk this morning will be recent advances in mode lock fiber laser using 2-dimensional MZine max phase as saturable absorber. My name is Harith Ahmad here, and my co-worker is Dr. Nora Serena Yusuf, Dr. Siti Aisyah, and our head of department, Professor Zurina Osman. I am attached in both places. Fortinet Research Center is a national center by the Ministry of Higher Education, and I am also a staff of physics department. Yeah. Okay, just to give you some idea, the outline of my talk, okay, is to look at application of ultra short pulse laser, and mode locking, how we get mode locking in fiber laser, basic principle of mode locking. I'm going to discuss very briefly. There are two approaches, active mode locking and passive mode locking. And then I'm going to go into a bit more detail, development of material saturable absorber. And then I will talk about MZIN structure, how we make them in our lab. And then I'm going to discuss saturable absorber integration scheme. I'm going to talk about 2 micrometer ultra fast laser and 2 micrometer thulium holmium dope pulse laser. And then I will go through briefly on the performance of TI2 MZIN and MACPHASE in terms of material characterization, fabrication, and then measurements such as nonlinear absorption properties, and then the fiber that we use, and then I will go to the conclusion. Can I move the slide, no? Okay, one of the most important thing why we do pulse laser is because there are many applications. There are tremendous amount of application of pulse laser, especially in particle acceleration. As pulse laser can produce ultra high electric field gradient, for instance, in application of isotope production, hydron tumor therapy, million electron volt ion source imaging, proton-based fast ignition. And then it has other applications such as metrology, measurement, stabilized ultra-wide bandwidth, for instance, in coherent LiDAR, optical clock, ultra-wideband communication, high-precision spectroscopy, and in material science, for instance, we can use for surgery, micro machining, chemical analysis, non-equilibrium ablation, and also as a second source, for instance, you want to generate terahertz. Terahertz is a very important radiation. Right now, terahertz is very important. For instance, you can detect drought, you can detect explosive. We have facilities in our laboratory for terahertz research. And also you can use ultra-short pulses for medical imaging and also therapy, extreme ultraviolet lithography, and biological soft X-ray. In media is remote sensing, remote tagging, directed energy, and advanced sonar. So as you see from this slide, there are many applications of ultra-short pulses. Okay, if you look into this slide, these are very important slide where we discuss. In the first slide, if you look at my pointer, the red pointer, the first slide discuss the conventional continuous wave laser. All right, these are typical laser. It can be the bulk solid state laser. We have a gain medium. So in the early days in 1960, the gain medium can be, for instance, a yet crystal, can be ruby rod, the gain medium, and normally the gain medium are being excited using a flash lamp. A flash lamp is somewhere around the same line with the gain medium. It will give an optical excitation to the gain medium. Therefore, the gain medium will be excited into the higher state, and then it will decay to the lower state to give out laser output as given in the red line here, laser output. This is a very simple cavity. It consists of two mirrors, the back mirror and the front mirror, and the gain medium, and also the optical excitation source. Now, for the ultra short laser, for short pulse laser, is slightly more involved. It has mirror as what we discussed in the continuous wave system. It has a gain medium, which is being excited by a flash lamp, or now we excite them using laser diode. And then you have another device called shutter. The shutter just control it by electronically. You can just switch on and off, so that at some instant the shutter is open and you have a very high energy, a high power pulse in a very short duration. So normally you will get periodic short pulses and many frequency, and sometimes can be polychromatic. So in the bottom figure gives you some idea how we generate the short pulses. So the shutter is the loss medium. The gain is the gain medium. So the loss medium can be controlled electronically. So when the loss is high, the gain medium will start to build up the population inversion, and then the short pulses will be emitted as given to you in this bottom figure at 0 time, after 1 cycle T, and a second cycle 2T. So generally the pulses from a pulse laser can be seen from this figure. The average power can be quite low, but the peak power can be very high. The peak power is very high. So the interest in ultra short pulses is because we want very high peak power. So when you have very high peak power, it means that if you have very high peak power in a very small area, you can develop very high intensity. So intensity are normally given to you in watts per cm square. So normally the intensity can rise into gigawatts. So they are very powerful beam, and it can be used in many applications like medical surgery. If you go to doctor this day in the hospital, they will use laser now for your medical surgery now. Most of them are using laser. For dental treatment, they are also using laser, because laser are very useful, and it's not like using scalpel, knife. When you cut the tissue, it will bleed, and then sometimes you can get excessive bleeding. Using laser, you don't bleed as much as using scalpel, but you can cut and then it will fuse at the same time, so you will reduce the amount of bleeding. So the other interest in short pulses is in micro machining. So normally the short pulses can make very deep hole, and very narrow hole, very clean hole, very precise. The word I'm going to use is very precise. These are being done by using short pulses in the femtosecond and picosecond. These are in 10 power of minus 15 and 10 power of minus 12 second. They are very short pulses. You can get a very sharp and deep and very clean holes that you can make. And normally short pulses laser are being used to drill stainless steel, all right? And if you make a comparison with the normal nanosecond laser and millisecond and CW, you can still make holes, but they are very large hole, and sometimes it looks very untidy. The holes, you have debris, and then you find that it has a large heating zone. Compared to the short pulses, you do not have the heating zone. Okay, if we go into in depth now, this figure will tell you a bit more. It's a very nice figure to show you the difference between using a nanosecond laser that can be based on Q switching. Normally, when you use a nanosecond laser, the pulse is about 10 power minus 9 seconds. You normally can make a hole, but if you look at this figure carefully, during the process of making the holes, you will have micro cracking, you create a shock wave, and then you have a very broad melt zone. At the same time, you have surface debris, you have something scattered outside the metal surface. So this thing becomes very untidy. It's not a very clean hole. So using a nanosecond pulses, you can still make holes, but it's not as good if you look on your right-hand side using ultra short pulses. normally in femtosecond or picosecond, you find that the hole that you can generate are very much deeper. They are very much deeper and they are very clean and they are very narrow, very precise hole. You can create a very precise hole, so you find that there's no micro cracking, no heat transfer to the surrounding matter, no damage surface, and no debris. So it's very clean. So people are moving, most industry, and especially in the car industry, using robotic, as what we mentioned, Industry 4.0. They are using machine now, and most of the car are being produced using laser. So they normally have a ultra short pulses laser, femtosecond, to do the drilling onto the car, on the car frame. So ultra short pulse laser can be generated using mode locking technique. Okay, mode locking is a technique used to generate coherent high repetition rate and ultra short pulse by virtue of phase locking of the longitudinal mode inside a laser cavity. I will not go into greater detail in this slide because due to time constraint, due to time constraint, and normally I will have a random phases. Now, normally, if you look into a laser system, the phases are random phases of all laser modes. If you have a Fabry-Perot cavity, you normally have an oscillating mode that can be generated. So the normal laser will have random phases of all the modes as you see in this figure. If you look at my pointer, if we go down to the next figure, in the mode lock, the word we use mode lock, we lock all the mode together at the same time. So when we mode lock all the mode together at the same time, so I have what I call as lock phases of all the laser mode. Eventually, you find that the phases are all the same. If you look at this figure, as you look at this, and these are called the electromagnetic wave. Number 1, number 2 electromagnetic wave. They are all having the same phase. So you lock them all together, and the output will be given a very sharp pulse, very high power with a very short duration as compared to the earlier case where you get random mode, the pulses peak are not sharp, but it's random as you look in this figure. So normally in a mode lock system, we have the gain medium, which is the amplifying medium. We have a shutter, we call modulator, that's open at each round trip. After one round trip, this modulator will open and allow the pulse to go through and to create the mode lock pulses. In between the round trip, the modulator will be closed and the gain will be taken, the gain build up will be taken by the gain medium. So this figure gives you some interesting how the phases are random as can be seen from here. Okay, so actively modulating the gain or loss of a laser cavity in a periodic way can be done by cavity repartition frequency, by cavity repetition frequency, by cavity repetition frequency, C/2 and L. N is the index of the gain medium to achieve mode locking. I just want to check, can you still hear me? Can you still see me? Hello?
Yes, Mr.
Can you see?
Yes,
Can you
sir.
see?
Yes,
see
of course.
Can you see me? Okay. Just to be sure, sometimes I'll be talking to the mic is not on. Okay. If you look at this cavity, I will have an output coupler. There's a front mirror. I will have a gain medium. I have a loss medium. That is my modulator, and I have the high reflector, the back mirror. What actually happened? The gain medium will be excited by pumping of light. You have to pump light onto it, either through diode pumping or flash lamp pumping, which I explained in the first slide. It causes excitation into the higher state. Eventually, it will decay into the lower state, and it will give you a laser output that will oscillate in between the two mirrors, the front mirror and the back mirror. The back mirror is normally 100% reflecting. The output mirror can be 70% reflecting. So the light will go back and forth into these two mirrors. So the loss mechanism, that is the modulator, can be controlled externally by the electrical current. Then you can switch on the modulator after the build-up of the gain medium to a large extent. Therefore, you will have a very large pulse that comes out. If you look at the pulse from intra-cavity can be very large, but the mirror is 70%, so you have a large pulse, but slightly smaller compared to the intra-cavity power. So in this figure, you can see between the first graph, the red graph is called the loss mechanism. It's given by the red figure here, by the red object in the cavity. Is the loss mechanism, where the loss mechanism is being controlled externally by the electric field by having an electro-optic crystal. We use crystal normally, electro-optic crystal that being externally modulated. So when the loss is at the minimum, if you look at this figure, you look at my pointer, the red pointer, when the loss is at the minimum point, you find the laser pulse start to be emitted, a very large laser pulse start to be emitted. And then when the loss increases to a high value, there's no pulse in between. And then the loss come back to a lower value, you get the second pulse, and then no pulse, and then pulse. By having this approach, by controlling the signal at your loss modulator, you can generate the mode lock pulses as given in the blue line of this figure. So normally you have very sharp peak as given in this figure, as I explained just now. You will normally insert something into the laser cavity that sinusoidally modulate the amplitude of the pulse. Mode competition couples each mode to modulation sideband. Eventually all the modes are coupled and phase locked. This is the technique how we do mode locking using active approach. When I say active approach, I have an electric field to control the modulator. Means this modulator is being controlled externally by electric field. All right. Now it's the same thing as I described earlier. If we do the same thing, but now we don't do using the optical, using the active approach, using electric field. I can do a similar approach by having a saturable absorber. It's a passive component. It's a passive. It does not need to be controlled externally by electric field. It's a passive component. Inside the laser cavity, through the mutual interaction between light, saturable absorber, and the gain medium, we can automatically achieve mode locking. So using saturable absorber is another approach. It's called a passive technique compared just now what I have explained, active technique. So the passive approach is just a saturable absorber. It's also a loss mechanism. So when the light that comes out from the gain medium, when the light that just come out from the gain medium can be of low intensity, this light will be absorbed by the saturable absorber. And as the light increases further, and then this saturable absorber will still absorb, but it have less absorption. As the light intensity increases to a very high value from the gain medium, the saturable absorber will not have any more molecule or atom to absorb the light. Eventually, this saturable absorber will allow the light to go through the back mirror, and then this light will be reflected back into the gain medium to be further amplified. Eventually, it come out from the front mirror to give us a very short, high power pulses, that what we term as mode lock pulses. So the idea is similar to the one that we described in the last slide. You have the loss mechanism. So the pulse is being produced at the point of the lowest loss, where the saturable absorber does not absorb anymore. It opened completely, and then the pulse is being produced, and then this saturable absorber will regain its state and it will absorb the light. There's no pulse. Eventually, pulse will come out at the second lower point and also at the third lower point. So normally you find that using saturable absorber is an interplay between the loss mechanism, the gain, and the gain mechanism. So normally we will insert something into the laser cavity that favor high intensity. This is the principle of saturable absorber. And one of the most important points about saturable absorber is you have strong maxima, will grow stronger at the expense of weaker one. Eventually, all the energy is concentrated in one packet. So the advantages of saturable absorber allow the generation of much shorter pulses. We can produce much shorter pulses compared to the active approach, and very compact and very simple all fiber structure, low cost and good compatibility with optical fiber system, which University of Padang is interested. We are willing to collaborate. It's very interesting area. It doesn't cost you very much, but you can publish very good publication. Normally, you can publish in the Q1 Web of Science or Q1 in Scopus. So most of this work are very interesting. I think give you an opportunity for publication and also for the academic of University of Padang to produce publication. And we are willing to collaborate very closely together. Now, I will go into details saturable absorber, which I have explained just now. For the last 2 years, we have been working a lot on saturable absorber. And if you look at this figure, hello. Yes. If you look at this saturable absorber, it started with graphene. It started with graphene 2010 discovered by Novoselov and Jam. I think they are now in Singapore. It has a zero band gap. It started from graphene, and it was discovered by accident. Sometimes great science are being discovered through accident. Sometimes you plan, you might not achieve so much, but along the way, you will discover something else. So graphene was discovered through accident by Novoselov and Jam in 2010, and they got a Nobel Prize in a very short span of time. So graphene is the first demonstration of two-dimensional material. And then along the way, you have other material like transition metal dichalcogenide. It has a band gap of 1 to 2.5 electron volt. And then you have phosphorine. Phosphorine is black phosphorus. It has a band gap of 0.3 to 2 electron volt. And then you have arsenic, 0 band gap, and you have antimony, also 0 band gap to 2.28 electron volt. And then you have BN, and then what we're going to discuss this morning will be MZIN and MZIN and max phase. They normally work in the infrared region, near infrared region. And then you have other material like bismuthine, band gap of 0.28 eV. So historically, the saturable absorber has been around for the last 30 years. It started from color glass. It started from dye in the 1960s when people do laser. They use dye, color glass to act as a saturable absorber to quick-switch and mode-lock laser system. So along the way, it has been superseded by a device called CSAM, semiconductor amplitude modulator. It's quite an expensive way to make because it needs very expensive equipment to fabricate the amplitude modulator CSAM. And one of the major suppliers now is Bartok. And this CSAM has been used for the last 20 years. It's quite a very active field in the early days, but now it's being superseded by non-CSAM such as quantum dot you can use, and 1D material carbon nanotube been done by Professor Yamashita. And then you have 2D material, which I've discussed just now on graphene, topological insulator, transition metal dichalcogenide, black phosphorus, and MZ. Okay, as I discussed earlier, I will go through quickly. In the early days of saturable absorber, it started with dye and color glass in the early 1960s. As early as that, they are the first generation of material saturable absorber able to induce pulse operation, but are bulky and less stable in the early days, the dye and color glass. Eventually, along the 1960s, you have carbon nanotube and graphene. Then you have CSAM, and then you have TI, topological insulator, a form of two-dimensional material, transition metal, dichagonite, 2D material, and black phosphorus. And this gives you some idea on the slide. We started with color glass, CSAM, and then it moved to low-dimensional material. Now, if you look into our MZ now, normally if you look at MZ and MaxPhase, they are very complex structure. Okay, it has a general formula of Mn plus 1 Xn Tx Mz. Normally N is the transition matter, X is the carbon or the nitrogen atom, T is the surface group. So if you look at this figure, you find that MZ structure can be in so many forms. It can be M2X. I think the thing is a bit small. M2X. It can be M2X2. It can be M2X3, and it can be N5X4, and so on. It can take many configurations. So in the first basic case, it can have 2 layers of the transition matter, sandwich the carbon or the nitrogen atom. These are in a single transition matter. These are in solid solution. These are the order of the MZ, as what you can see from this figure. These are schematic illustration of MZ structure, and this is what we do in the lab. We tend to fabricate MZ by ourselves from MaxPhase. So as given to you in this on the right side, the general formula, the value of N can vary from 1 to 4 depending on.
Itu pasti gua harus ngomong dong sayang nanti.
Yes. Hello.
Yeah. Sir?
Are you saying something?
Not really.
Okay.
Just continue.
Okay. Okay. If my time's up, please inform me. Okay. Depending on the number of transition matter layers and carbon or nitrogen layers present in the structure of MZ. So solid, you can use them either in solid form or you can use them in film form. We will see how we put them in our cavity. So this is how we fabricate from this figure. You can see from the slide. It's very interesting. Normally we spend about 2-3 days to fabricate the material. For MZ, we normally start with a MaxPhase precursor, and then we do the process of wet etching, and then it moves to. If you look at my pointer for wet etching, and then you have multi-layer MZ particles. Sometimes you can have direct delamination through various methods to form the 2D material of MZ. This is the process which we fabricate ourselves. So normally in the etching process, you can use hydrochloric acid and lithium fluoride. Sometimes people use hydrofluoric acid, but it's quite dangerous because hydrofluoric acid can get into your bone. So we avoid using that. So our etching are based on hydrochloric acid and lithium fluoride. Eventually we will produce, as you see in this on my pointer, the rightmost, I produce Ti2CTX. They are 2-layer material. They are 2-layer materials. I produce from the MaxPhase. I can get MZ 2D layer. So first approach, the MaxPhase is selectively etched in fluoride ion containing acid, multilayer MZ particle, or in situ delaminated 2D flake using the MUL method can be obtained. Second approach, I can go through MaxPhase selectively etched in molten salt. The product we produce are multi-layer MZ particle which can then be delaminated through intercalation technique. You can check our publication. We have produced quite a lot of publication, about 150 publication on the saturable adsorber for the last 3 years. All right. Now, these are, I will not go into greater detail because I am very concerned to limit my talk to half an hour. So normally, this is a very nice figure to show you the mix termination until you have bare or uniform enzyme layer. So the advantage why the interest of enzyme, it has high electrical conductivity and mechanical behavior of transition metal carbides, nitride. It has a functionalized surface that can make enzyme hydrophilic and ready to bond to various species. High negative zeta potential that will enable stable collider solution in water. Efficient absorption of electromagnetic wave, that's what we use for saturable absorber. Highly tunable and tolerable electronic optical properties. So this is the interest of MZ because it's very flexible the material. The one that we are looking at is purely on optical work, on optical behavior of MZ. All right. Now, MZ as a mix, as a saturable absorber is given in this slide. If you look at this figure, I think the slide is open to be shared. You can use this slide. It can be used for energy storage and harvesting, the two-dimensional MZ. But the most important thing that I want to emphasize in this talk, we use MZ as a saturable absorber. It has a broadband behavior, band gap 0.8 to 1.8 micrometer, nonlinear optical responses with increased transmitted at higher light fluences. The large band gap tunability suggested lower optical attenuation compared to the well-known graphite. Graphite only have about 2.3% per atomic layer in terms of absorption. So MZ has a much higher value. So MZ is a very interesting alternative compared to graphite. Of course, the first demonstration of 2D material as a saturable absorber in the early 70s was using graphite actually. So now people have moved to other material. It's a very hot area. A lot of people, I think, working in this area, saturable absorber for log fiber laser. It has a large surface area and good electrical conductivity and stability, high photothermal effects. Now, how do we do that in our lab? Now, if you look into this figure, it's very interesting. Besides making our own MZ, we make everything ourselves here. We borrow the chemistry lab to fabricate the material. And then we, of course, you can use this material as a thin film to put in front of the fiber to generate the mode lock. But we prefer to use it onto a tapered fiber because it can take higher power. And they are more interesting compared to the thin film. So we spend a lot of time on tapered fiber, as you see in this figure. If you look at my pointer, I have a D-shaped fiber. That is been done very simple. I think University of Padang can do this. These are very cheap. They are very cheap experiments. So we have 2 stages, and then we have a flame. What we do, we melt the fiber. We take a single mode fiber, we strip the coating. We are left with the cladding and the core, and then we put the flame. We soften the glass, and then using the stages, we pull the fiber both ways. Eventually, you create a very small diameter core, a very small diameter, about 8 or 5 micrometer. From 125 micron, you reduce to 5 to 3 micrometer. So these are very low cost experiment, but it's very productive, I would like to suggest to the academic of University of Padang in this conference to explore to do tapered fiber. So eventually the tapered fiber looks like this. So you look at your left-hand side, the fiber of the original shape, it has a cladding about 125 micrometer, the core about 9 micron on left and right. After putting the flame, soften the fiber, I pull the fiber, I will get a lower diameter, about 3 to 5 micrometer. So normally what we deposit the max phase, for instance, TI2C or TI2ALC, because max phase has an aluminum here, Amzine does not have an aluminum here. So we will coat them. This is how it looks like in actual photograph. In the D-shaped fiber is much more simpler. What we do, we just buy a motor, a cheap motor, a simple motor, and then we wrap using a sandpaper, a very fine sandpaper around the motor, and we drive with 12 volts DC. Eventually, we bring the motor very close to the surface of the optical fiber. Eventually, it will cut. It will cut the optical fiber. If you look, it looks like arc shape. It looks like arc shape. It cuts fiber, and you have the core somewhere around here. The core is right in the center. So now you have an empty space here. What actually happened? We will coat with Amzine or Max Face. What takes place in this approach, tapered fiber? If you look, the light will come to the core. Electromagnetic wave will travel in the core, and you find that certain percentage of the light will travel in the cladding. In the normal optical fiber, the single mode fiber, about 10% of the light travel in the cladding, 90% will travel in the core. The core is of dimension 9 micron. 9 micron means 90% will travel in the core and 10% will travel into the cladding. As you cut off the cladding, if you cut off the cladding as shown in this red pointer, you cut off the cladding. Now the light, a big portion of the light, maybe about 40-50% of the light will travel in air, Now, what if Amzine, I put Amzine in this hollow area, I coat with Amzine saturable absorber in this hollow area. The light now, the effervescent field of the light now will start to interact with the saturable absorber and will generate the mode lock pulses. After what comes out on your right-hand side now will be short pulses, mode lock pulses. It will travel in a ring cavity. It will generate. So the whole idea is to use mode lock pulses in fiber laser. If you opted out for using the motor just to cut off the approach. And we also do work on thin film. Thin film, we normally put the saturable absorber in polymer, which is PVA, and these are casting technique polymer and POO. Now, the next interest, beside the saturable absorber, we are also working on a very interesting wavelength, the 2 micron. Now, you can do this work in 1.5 micron, you can do this work in 1 micron, you can do at 1.3, but our main interest currently, the last 1 year, 2 years, is 2 micrometer. Why are we interested in 2 micrometer? Why are we doing work on 2 micrometer? Because 2 micron fiber laser, it covers a wavelength range from 1,700 nanometer until 2,100 nanometer. And the 2 micron laser has a very high absorption for carbon dioxide gas, which makes them suitable for sensing application. If you have an oil and gas industry like in Padang, in Sumatra, you have a lot of oil and gas field. So carbon dioxide is there. You want to send the carbon, you want to detect the amount of carbon dioxide. So 2 micron fiber laser are very useful for sensing application. The 2 micron laser also have very high absorbance in water. It operates in eye-safe region, thus making them useful for medical surgery. Right? If you look carefully, we are looking at the mode lock fiber laser to be used for tissue, to do tissue cutting. This is a tissue now. We can cut a nice rectangle in the tissue. This is a bone. You can cut in a bone actually. So 2 micron has fantastic application in medical surgery. And right now we are asking for funding for dental surgery, for soft tissue surgery actually. So we are looking at 2 micron mainly for medical application. Now, the 2 micron, normally we use thulium holmium cold doped fiber. It's a gain medium. It comprises of two rare earths. Thulium is a rare earth, holmium is a rare earth. Now, thulium, holmium are co-doped in a single mode fiber. If you look in this figure, it's a very important energy level diagram. Normally, we pump our thulium at 1.6 or 1.56. You get an excitation from this lower state, from 3H6 until 3F4. You can get the excitation now to this point in thulium. And then because there is similar energy in holmium, so I will have an energy transfer from this 3F4 state to holmium. Eventually, I will get the wavelength. Why I'm doing this approach? If I can use thulium, but it has a limited wavelength range of 1.8 to 2 microns. Sometimes you only get about 1.9. You only get about 1.9. All right. Now, it depends on the quality of your optical fiber. If I use holmium, I can generate a longer wavelength. So holmium can give me a wavelength from 2 to 2.1 micrometer. So what I'm doing now, I have a two-step excitation. I have a laser diode that pumps the thulium into the higher state. Then it cross excite the holmium into the higher state as given into this figure. Eventually, it gives you the output in 2 to 2.1 micrometer, which is very useful for medical surgery. So this figure, short of time, I will not go into detail. The different rare earth element in oxide glass in a single mode fiber. Sometimes you find that you can also have rare earth in fluoride glass. It has a slightly longer wavelength. The best wavelength for medical surgery is about 2.9 micron. About 2.9 micron.
Professor Aris,
Yes.
we got your time for presentation. It's going to be a bit over.
Well, I have to stop now. Or what? Hello.
Yeah.
It's not very
Our
clear.
time for presentation, I thought.
Okay, give me about give me
That's
about
okay.
5 minutes. 5 minutes. I will wrap up my my presentation.
Go on.
Okay. Okay. Because of time constraint, I cannot go into greater detail on the MZIN and max phase. My sincere apology because time are very limited. And this slide gives you a very interesting idea how we share our idea. We are sharing how the process, we are sharing how our process, how we fabricate. For instance, MZIN, how we make max phase, the various method. All right. And these are the Fourier transform that we have in our department. We have all the equipment to do Raman, X-ray. We can also do the SEM and HTM. We have all the characterization equipment for the material. So these are typical results that we have. And this from FESEM, field emission scanning electron microscopy of how the max phase looks like, how MZIN looks like. Since that I'm not able to go into detail, this is how it looks like in terms of how we put the MZIN onto the tapered fiber. Okay, and these are typical measurement where you have to measure the most important parameter in this type of work, saturable absorber, are the position depth and also the saturation intensity and also the non-saturable loss. All right. And these are the typical cavity. I just go through this quickly. I have two laser diodes that cause the excitation in thulium holmium dot fiber laser. This laser diode is at 1560 nanometer. It will cause excitation in thulium, and then it transfer energy from thulium to holmium. And this is my saturable absorber here. You like my pointer, my saturable absorber. And we have a PC to control the state of polarization. These are typical result that we get for MZIN and also max phase. And we give in this last slide, it's very important last slide where we make a comparison. It's very important to compare your work. And from this last slide, I make a comparison. We make a comparison between MZIN max phase compared to other 2D material. These are all 2D materials, and the one that we are working right now is zinc X-ray. We make a comparison and different configuration and the different output wavelength and signal to noise ratio, and also the pulse wave. These are the pulse wave in picosecond. In our work, we get about 1.6 picosecond. So I think that's all, if I'm not mistaken. Okay, this is our publication and so on. So thank you very much. I am open for question if anybody want to ask question.
All right, thank you so much. That's the Professor Harif. Maybe a participant wanted to say something or asking something? Oh, if you have any question, you just click below on the chat room and write on the chat room. Right. Maybe we got to move on to the second presenter, keynote speaker. It's just because we got, got a tiny time, but that's okay. If you had any question for Professor Harris in the next moment, they're running by the time, that's okay. Just click below on your chat room. And right now we got to move on to our Professor Wilson. Professor Wilson, are you?
Yes.
Gonna, yeah, that's wonderful. Wait a minute, can we remove the presentation of Mr. Harris? MIT, would you like to help me? The screen is getting off. Yeah. All right. Ladies and gentlemen, for the second hour keynote speaker, it's from Japan. We call that Professor Wilson. I'm not sure. Oh, yeah. Professor Wilson, absolutely, as a graduate from De La Salle University Department of Physics from Philippines, is that right?
Yes.
All right. And then right now, going to the doctoral as a doctor on engineering, Department Osaka University. And of course, Professor Wilson, wow, it's incredible because he was awarded many awards, and which is such as like the first international symposium on automatically controlled fabrication technology as a best poster award. And for the best poster award category, Professor Wilson scored the many award, which is like the Vacuum Society of the Japan, 46th Vacuum Society of Japan Annual Symposium, outstanding for poster presentation. Right now, we got to take a look at our Zoom. It's running to surface or interface. Wow. Right now, Professor Wilson, time is yours.
Thank you very much for the introduction. So my name is Wilson Ajiri Coutinho. I am now at the Department of Applied Physics, Osaka University. And if you want to contact me, this is my email address. The topic is, the title is Surface Interface as a Playground for Exploring Physical Phenomena and Foundation for Realizing Design Materials. And I will use hydrogen surface reaction as a study, a case study. But as you see from the content of the abstract and also from the title, you no need to be serious about the content. I will not go into the details, but I hope you will enjoy. I will just tell a story. First of all, I would like to express my thanks to the organizers. So, distinguished guests, dear teachers, fellow students, and friends, I came to pay my respects to you. There is nothing I respect more than someone planting trees under whose shade they may never sit. So I think this is what the spirit of education is. So you are investing on something that you may or may not, or even for research, you're investing your time, your effort, everything on something that you believe in, but you may not be able to reap the benefit from. But still, I think it's a very noble cause in some sense. And just in case I will not be able to finish the topic or the talk, I would just like you to remember that what we are doing is we do the design of materials. Why we do this is to control energy. And finally, why we do this is to sustain life, etc. Everybody, I think, is doing that. And then, but we are now at the stage where we can be doing the design of materials from function to realization and going forward or going in the reverse way, using, of course, the natural materials that we have, which are given in the periodic table. So, to go further, to proceed, I ask you some questions. For example, a general question is why we study physics, why we study mathematics, why we study something. There are many reasons, I think, or you can give some altruistic reason for this. But just to lighten the situation, I would like to present some schoolboy motivation for studying. To that, I give you this figure. This character. These are two characters. For those who can read this in Chinese, it's Qi Gong. In Japanese, it's Qi Gong. In English, it means life energy. For those who are interested in animation, manga, you know Demon Slayer, I think. In the movie, there is Demon Slayer. They can do some
Demon Slayer.
Or some power. It's like some form of Qigong. And then I give you another word. This is in Chinese, it's read Lian Jin Su. In Japanese, it's Renkin Jitsu. In English, you know this as alchemy. So these two words, my schoolboy motivation. When I see, oh, I want to study, I want to have this. But the question is, what are these? Are they magic or are they science? What is the difference? Are they reality or something? So,
Jepang ini, what is science? Magic and science judulnya.
what is the difference? So the question is, what is the sorry. So what is the difference between magic and science? There are many. You can give some many reasons, but I want to quote this one by Clarke. So Arthur Clarke, the novelist, he has the laws, and the one that will answer our question is the third law, and it is any sufficiently advanced technology is indistinguishable from magic. So you see something, some phenomena you cannot explain. Oh, it's magic. For example, now you have iPhone or you have some smartphone. If you bring your smartphone, let's say, to 17th century or 16th century, it will be magic in some sense because people don't, it works, but people don't know how it works because it's so advanced. So the difference between magic, I think, is simply magic you can explain. If you see something, if you see something that you cannot explain, it's magic. But you have developed it into a level where you can explain. It now becomes science. So why we study is to develop our understanding from a level of magic to a level of science. That is, in some sense, my schoolboy motivation for studying. But you can say, oh, it's so simple. So there is also a grown-up version of this question, why we study. A grown-up motivation would be, for example, we ask the question, what is the difference between living things and non-living things? Some biology, very basic biology. Or, for example, some physics. What is the difference between the ground state and the excited state? And remember the question, why we have to study. So my answer to this is there is a relation. Living things are in the excited state. Non-living things are in the ground state. So what does this mean? In order to sustain living things, they need energy. Non-living things, for example, the rock and so on, they don't need energy to maintain their current situation or their current state. So why we study? One reason is because of survival. We need energy. And what is the relation? Very simple. Energy means resources, food, etc. So in some sense, we have to compete for this. And then before, it's very easy. When you say competition, it means eliminate the competitor. Then you have energy to use for your own. But then history says it's not really very efficient. So we have to go into a different level. And that is to study. And so, but the question is, so you know now that we need to survive. How to survive? And I said again earlier, it's all about energy. Energy. Again, it's energy. So we need energy to survive. Energy to survive. Then I mentioned earlier how to control the energy. How do we control energy? That is the next question. And then we can get some answers from history. Remember, in history, we have Stone Age, we have Bronze Age, and something in between. And now we have Silicon Age, for example, in allusion to the Silicon Valley. So you know more or less what is the direction of the discussion. It's matter or materials will help us control energy. Well, what is the difference between matter and energy? Basic, again, in physics, very basic physics. So we know matter is anything that has mass and occupies space. And from the first law of thermodynamics, we know about the conservation of energy. And Einstein already said, rest mass is equal to, there is a rest energy, and it's equal to this, it's given by this equation. And finally, it means matter is energy, or energy can be matter and so on. So we use material. And then we have to remember, now we realize, oh, why the first lesson we learned when we took up physics or science was matter, motion, energy. It's like a mantra. Matter, motion, energy in this sequence. Or at least that's how I remember physics, the lessons I got. It's in the sequence, matter, motion, and energy. And then now you know that how do we describe matter? It's a periodic system, a cluster, or whatever. And then how do we describe motion? Then we start to learn Newton's laws of motion, or classical mechanics, or quantum mechanics. And energy. Now we start to also statistics, how energy is distributed into the the parts of the system, etc., etc. But still, it's always matter, motion, and energy. Very broad, and then we go into the detail. So why study? Again, just to summarize the first part. Why do we study? We have to do survival, we have to control energy, and we use material. And then, remember, so how do you use the material? So we particularly use the surface. And we use some first principles. Principles are rules and assumptions that we cannot do without in order to proceed with our discussion. For example, the things that you would initially learn would be variational principle or principle of indistinguishable particles and so on and so forth. So what? Then you start to ask, so what? So with this, we can, for example, because it's research, so we can start to ask some fundamental questions like, is this formula correct? Or is water H2O? So some fundamental questions we can do, and then we can use the surface to play around to do this. So the surface becomes important because the material has a surface, and it's only through the surface that any reaction or anything can happen. It starts at the surface or the interface between two materials. So it's important. And then this is just a picture of how the surface would look like if you zoom in. And then, of course, there should be always a set of experiments that come with study of the system. For example, here, again, I go back to this equation. By the way, I would like to mention that in this, for example, in this chemical equation, the most important part is not the initial product, not the initial reactants, not the initial, it's not the initial, of course, the initial reactants are important, the final products are important, but the most important part is this arrow here. Here is, I call imagination. We don't know what happened from initial reactant to final product. It has to be imagined, and this has to be filled in. So that's why we can ask the question, oh, is this correct? Yes, maybe. Because in experiment, what we can do is before and after. We can observe what happens before and what happens after. And we have to assume in between, we have to develop something and check the ideas of what is happening in between. And then this is an example. And it turns out, for example, in this case, for those who are interested, it's not true. You need actually this water. You have to have this to be really, to understand really which element comes from which of the reactants, etc., etc. But I do not go into the detail. Also, another history. I mentioned earlier about is water H2O. Ever wonder how they find this out? It's actually a chemical set up like this by Dumas. So he set out to determine is H2O, water, 2 parts hydrogen, 1 part oxygen, and so on. Yes, he found out that it is so after doing this experiment. But yes, like most good experiments, this experiment set out to set a question and was able to answer that question. But like with very good experiments, it has some added value. And what is that? Is that it posed a more important question. The question was, oh, here you see copper oxide powder. Dumas found out that if you change this to another material, the amount of water that is produced changes. But he doesn't have a reason or answer to why it is so. And he found out, for example, that, remember this is 1843. And then the names, finally, 100 years later, there is another 2 paper by Taylor and Leonard Jones. So it took 100 years for the answer to come out. And the reason is very simple. It's all about the energy of the system. For a different material M, with reactants A and B, depending on the material, the energy changes. The energy, so this is, without going to the details again, this is the energy scape or energy landscape of the system. And then you see what is important here is actually, if we zoom in, is this part. And if I draw this, you immediately see, what is this? This is a potential barrier. It's a potential barrier for that you study in quantum mechanics 101. So very simple, it's just a barrier. So any reaction is, when you think of it as initial state to final state, there is a transition state that you can look as a potential barrier between the initial state and the final state. And then for any reaction, you have like this. And then the most important part here, like I said earlier, the initial state, it's given. You have some material, it's given. But you want to get a new material, the final state, it's also given. Nothing we can do about this. This is what we are given, initial state. The final state is what we need. Nothing we can do. But there is this transition state, the imagination part. This part we can do a lot about. So I say this part is the design space. The design space of the system. And how does this look? This is potential. Energy of the potential. So for example, if you are into, you can look up, for example, the relevant potential energy of the system. It depends on the component. And then you can solve the Schrödinger equation and so on and so forth. So just for hydrogen, for example, it looks like this, just to show you. And then you can do some calculations that correspond to this. So just going very quickly. So you will see that the energy, so this is the energy landscape that I am talking about. And then you see how the reactions will change depending on the position or where the reaction is on the surface. So different configuration, different shapes. Same reactant, but different materials, different surface materials, you see again different shapes. So you can do some energy scaping or as compared to landscaping with the surfaces. So this is, I think, how we use material to design or to control energy is by doing this energy landscaping. So what, for example, I will skip some of the parts. So just to point out, I use hydrogen because to do the modeling, because to understand hydrogen, it said that is to understand all physics. Not me, but somebody said like that. And to understand hydrogen, one must also understand the physics. Is another paraphrase. So hydrogen is a good system to test some ideas, and also you know how hydrogen, what the role of hydrogen is in the history of physics, for example. But then it's not true that we already know everything because it's still being discussed. Is hydrogen really in the correct place in the periodic table? Or where is it? Where should it be in the periodic table? If it should be the first element or what? We still don't know. And it's not yet. So what? So we can actually use the surface to use hydrogen to probe the surface. For example, you ask the question, can we hydrogen distinguish between these two? This is nickel aluminum 111, and this is copper 3 palladium 11. And then if you shoot, will the be distinguishable? Answer is yes. So this is just seeking probability. Shoot hydrogen on the surface and determine how much is being scattered. And then you see the property changes depending on the material that is being the partner material that is being shot on. So you can see that it is possible to probe. And yes, theory and experiment, they agree. Also, you can use this to align molecules. For example, hydrogen molecule you have, but then they are mixed together, but you can use them as filter, the surface as a filter. For example, after passing through copper 111, let's say, you can see that helicopter-like rotating molecules will come out faster than cartwheel-like rotating molecules. So something that you can play around with. And you can also do this by scattering. And finally, sorry, this is just to show a real example is how to efficiently produce hydrogen ions, H-. So the reason why I show this is because of energy. There is nuclear fusion. I think the idea of nuclear fusion, but why we do not have it the same as nuclear fission reactors. The most important part is because we cannot produce efficiently and reliably H- ions. And this is the reason. So here, for example, there is hydrogen atom interaction with tungsten is the wall of the nuclear reactors. And then cesium is some material that we use in order to do something.
Professor,
Yes.
we got the
Yes.
3 minutes more. 3 minutes.
Yes, yes. So I
That's
will
okay.
finish in just 2 minutes. So this is an example. So this is the reason. Remember, we want to get H-. H- means get electron from the surface. So we want to get electron from the surface, and how to do that? What we need to do is to have when we want to produce negative hydrogen ion is to produce to get material that has low work function. So tungsten, like I said earlier, tungsten is a given material. It's the wall of the nuclear reactor. So we cannot do away with that. And then, but we need, where is, so this is the periodic table. Where is tungsten? Here is tungsten. Here is cesium. So tungsten has a work function of 4.5. So this is the much energy that you need in order to get 1 electron. This is cesium. It has this much work function. It has a lower work function than tungsten. So what if we do some alchemy? Mix this with this, what happens to the system? So this is work function as a function of cesium coverage on, so we decorate cesium with tungsten. Tungsten with cesium. So this is the value of the work function when there is no cesium. It has the value of the work function of tungsten. And when we saturate the surface with cesium, this is the work function of cesium pure. It's 2 point something. But the interesting part is when we go into mid-range of coverage, we see a work function that is much better than what was the original element for the system. So here it's the lower, it shows a lower work function. So in some sense, some material designing with some property that cannot be found in nature just by mixing two materials. So yes, of course, you can check that it is indeed the case, and then you can check for other alkali materials. And then, but cesium, decorating with cesium produces the lowest electron negativity, or the easiest to pull electron out from. And then yes, you can check what happens to the system and so on and so on. But still, it's not perfect, and there are some things that are still going on. And you see that the quest is still continues, still not yet. And then you can also do some scattering on some materials, also probe with hydrogen, and also change the, let's say, electronic and optical property of some material. also doing the same thing. So I finished. Sorry for taking too much of the time. And then I finish with this slide again. Thank you very much for your attention. Okay. So finish. And then there is a question. How can we manipulate a material in the transition space? Yes. So like I said earlier, it's this, sorry. So I'm now asking one question that, answering one question that was posed in the chat. How can we manipulate a material in the transition space? So the transition space earlier I said is the surface of the material. So this is actually the example. Sorry, I cannot move back. So this is one example of the transition space. We use the surface. So this is in some sense designing. We change the property of the surface by combining two materials. So actually the heart is also shown here. Yes. So let's say you want to have some function. So you want to have a material that shows this property. What to do? The usual way to do is go to your periodic table. Recall all the physics and chemistry that you learned in until you are in all the physics and chemistry you learned in college until your university education. And then start doing combination. So one strategy is combine A with B, check the property, structure, and then get the property, and then see whether or not you get the same function or not. If not, go back to this loop and then revise your materials and so on. I think this is one example was the one that Professor Harit Ahmad presented earlier. He showed max materials, max space materials. So x n plus 1 x and so A, B, C material, and then with different compositions. I hope it answered the question. Any other questions if you would like to ask?
Okay.
Thank you.
Okay.
Yes.
Is that done, Mr. Wilson?
Yes.
Okay. Per Wilson, how can we manipulate material in the transition space?
Yes. So that was yes.
Sudah dijawab tadi. Terus ini ada lagi. So we got another question. Wait a minute. Let me check. Here we go. Oh yeah. Oh yeah. Oh, it's not enough. All right. It's
Yes.
because we got a tiny time. So right now, do you have any closing statement before we go to parallel season? Prof. Wilson?
No. Yes. So I think it's not, the time was not enough to share everything. If you are interested, please contact me by email. It's I think my address is in the book of abstract. So please just mention that you are participant of this conference, and then the questions on. Yes, and welcome to visit us anytime.
Okay, that's wonderful. By the way, are you original from Japan or?
You said already. So I'm from the Philippines. That's why we have the same color.
Oh, mabuhay.
Mabuhay, yes.
Mabuhay.
Mabuhay.
That's okay. Thank you so much,
Thank you.
Mr. Wilson, Professor Wilson. But before we really go out, we're going to come back to Professor Harith. Are you still here? Prof. Harith? Datuk? Sudah pergi ke? Terkejar makan ayam goreng ni. Tak apalah ya. Baik, that's okay. Ladies and gentlemen, thank you so much. Prof. Wilson from Philippines, but you are right now is presenting from Japan. Right. And then it's time we gotta move on to parallel season. Thank you so much. What do we call that? Mahal kita maybe. No. Anyo. Just mabuhay. Right. We gotta move on to the parallel season. Ladies and gentlemen, Bapak dan Ibu, sesaat lagi tim IT kami akan berbagi Bapak dan Ibu sesuai dengan room. We got the 10 rooms. Nanti each one of the room, we got the one moderator, and also they are going to be operator also again in the work. And right now, we got to split you to join each one of room, and our IT team is going to be command and directly to make you to split and join that each one of the tent of the room. So is that okay? We got to move on to parallel season. Committee, Team IT. Are you ready, guys? Team IT. Yes.
Okay.
We are ready.
Ladies and gentlemen, you just got to open your room chat. You just click below on the which one room you wanted to check out and check in. Join, I mean. Yeah, that's right. Based on my information, if you wanted to join in that room 1 until room 10, you just pick up one of them. Which one you want? Which one your room? Yes, the moderator, don't forget to, you also join that room. Just pick up the number, Remember, if you have a number 01, it's the meaning of you in the room 1. 02, you're in room 2, and 03 until the 10, it's the meaning of, yeah, here we go. Nah, that's okay. Where's my screen? All right. We got a 10 room. You just click which one you wanted to go there. Now, let me check until the down. This one. It's a room number 1. It's number 2. Room number. So in front of your Zoom application, we show you breakout rooms from room 2, 3, 4, 5, 6, 7, and until the 10th. You just pick up which one you wanted to join. Just click join on there. And you already joined that room. Just click below which one the room you want. Remember, if you the number 09, you're going to be room number 9. Just click room 9. If you number 10, you just join to the room number 10. And that's to be continued. We're going to hold you until the 12, until 12 and 30 to parallel season on that room.
Test.
And I hope so you guys are ready to click join on there. Jadi teman-teman silakan klik joinnya di room mana teman-teman ada nomor berapa 1 sampai 10 teman-teman Bapak dan Ibu tinggal pilih aja mau join di room berapa. It's number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9, and number 10. You just click below on the click join in front of your breakout room. And that application is going to be progress you to join that room. And then after that, we get separate until the 12 and 20. 12 and 20 for today. Is that okay? All right. See you there. Ini udah boleh banyak yang gabung. Tapi di room 6 masih dikit. Dan untuk teman-teman mahasiswa, silakan pilih mana yang sesuai dengan tema teman-teman. Teman-teman masuknya temanya di mana? Minatnya di mana? Research-nya, paper-nya, teman-teman di mana? Silakan pilih 1 sampai 10. Ini room 6 masih dikit, room 7 masih dikit, room 9, 10 masih dikit. bisa dipilih. It's a feel free. If you are student of university, you just feel free to click which one the room you want to, and making like a synchronization with your maybe your passion, maybe your paper, maybe your topic, maybe your research, and we beckon you to click that the breakout room, and that application is going to be making progression soon. You join that room you pick up before. Right? Room 7 masih sedikit. Room 4 juga masih sedikit, room 3 udah banyak, jam 2 udah banyak. Room 1 paling banyak sekali. I don't know why the number 1 room, it's a first room, so it's many participants join the room. I don't know. Okay, you can click over here. So many people hasn't already joined. Would you like to join there? Jadi buat mahasiswa BP 2021, silakan pilih room mana yang saudara inginkan. Saudara tinggal pilih mana yang menurut saudara adalah minatnya dari saudara, dari 1 sampai 10. Yang 2020 juga gitu, 2019 juga. Silakan pilih dan silakan masuk ke dalam. Oh gitu. Room 1, room 2, room 3 itu fisika murni, atau fisika maksudnya, ilmu fisika. Terima kasih advice-nya. Terus yang pendidikan di room berapa? 4-10 pendidikan. Oke. Pendidikan 4-10, yang fisika saintifik atau ilmu fisika ini 1-3, 4-10 adalah pendidikan. So based on that data, we got room 1 until room 3. It's a topic all about the scientific or basic science, and room 4 until the room 10. We call that for the topic education of physics. Alright. Masih belum? Ini masih banyak lagi yang belum bergabung. Silakan bergabung secepatnya. Ya, ini sudah langsung dimulai. Pastinya di masing-masing room. Jadi teman-teman tinggal klik mau di room yang mana join-nya. 1-3 adalah untuk topik fisika murni atau ilmu fisika. Room 4-10 adalah topik untuk pendidikan fisika. Yes, thank you. Sudah di progress. Thank you so much. All right, so we're just waiting for so many people not really join that. What happened? If you need help, we can do. Yang di 2020 ini gimana ini? Belum ada bergabung? 2020 silakan pilih, kalau yang 1-3 itu untuk pembahasan topik fisika murni atau ilmu fisika. Kalau room 4-10 adalah topik untuk pendidikan fisika. Teman-teman BP 2020 masih banyak di sini, 2020 dan 2021 silakan diklik. Yes, I know. Thank you so much for the progress that I recorded. 19, 18, ini 2018 masih belum lagi bergabung. Silakan. Ya, silakan bergabung. Karena di room ini tidak akan ada aktivitas dulu sampai nanti setelah selesai trial session. Right, terima kasih yang sudah bergabung. Masih ada 52 lagi yang belum bergabung. Let's go immediately. And it's time to me take a break for this moment and this business. And then see you when I see you again next on the 13:30. Ya, ya, oke. Nanti kita ketemu lagi pada pukul 1:30. See you.
Nah, arah telapak tangan
Kami berkumpul untuk maju, jiwa bersatu dan tekad demi tujuan yang mulia. Kembangkan ilmu-ilmu fisika, tunjuklah di dharma kampus kita. Tunaikan kewajiban sivitasnya agar tercapai cita-cita. Mengabdi pada nusa dan bangsa. Fisika warisan ilmu eksakta. Fisika dalam panji biru FMIPA. Tunjukkan sikapmu, tunjukkan karyamu, bersatu dalam hati, senada dalam jiwa fisika. Fisika warisan ilmu eksakta. Fisika dalam panji biru FMIPA. Tunjukkan sikapmu, tunjukkan karyamu, bersatu dalam hati, senada dalam jiwa fisika.
Iya, Pak.
Dalam hati, senada dalam jiwa fisika.
Hidui dan kini ko umpamo buruang jika kata bangsa yo kinilah senteang muka sui hati hendak tabang mambu buang lah nampak padi masak di lereng gunung sayo maradai bakata bang padi nan masak takkan najuo kamano badan dan kabat tenggang tiado kawan maraso ibo hidui dan kini ko umpamo buruang jiko kata bangsa yo kinilah senteang muka sui hati hendak tabang mambu buang lah nampak padi masak di lereng gunung. Bandung ratonyo si unggeh bondo kabake sia kami minta tolong padinan masa disabi urang maratok hati di dalam badan sayonan senteng kadipangakan dua tamanu dia teh dahan tapaso paru anan basang pikan bayi tu bana kini nasib nan malang dua bamanuang mangana untuang takkan nama so dulunya pandai tabang tabang mambu buang bagurau samo gada.
Yeah, come on. 1, 2, 3, 4. Bacando buruang badang atso taman muang anta apo panyabab bamanong sambil tagan tuang diara kaki surang diri sambil membawa untuang ayam atau badarai tangi ko sambung menyamuang janji tanyo di tujuan kama kaki malangkah menyipatkan sungguh kaki dah indah tantuara pangana kasawan tapi tiba di pasar bawah kama urangan dulu kian tapi kini malenga santano baitu nasib indah dan tarui mangalo dia kato jawa kasih sia sepeda tarui dan kayu tarui bajuang dari sebuah ke sebuah untuk bisa buktikan tagak surang dua hasil palua.
Hidup dan kini kau umpama buruang jika kata bangsa yo kini lah sendel muka sui hati hendak tabang mambu buang lanam papa di masak di lereng gunung sayo maradai ba kata bang padinan masak dan masak takkan ajuang kamano badan dan kabat tenggang tiada kawan kawan marah soibo hidup dan kini ko umpama buruang jika kata bangsa yo kini lah senteng muka sui hati hendak tabang mambu buang lanam papa di masak di lereng gunung Bandung ratonyo si unggah bondo kabat kesia kami minta tolong takkan alai takato tido padinan masa disabi urang maratok hati di dalam badan sayonan senteng kadipangakan dua tamanu dia teh dahan dapat soparu anan basang pikan bayi tu bana kini nasib nan malang dua bamanuang mangana untuang takkan nama so dulunya pandai tabang tabang mambu buang bagurau samo gadang. Sampai jalan Balimpi nan basuh hendak menjalan buat sarai entah di majalanan kaluru tak bedo malah badan dia tio kakok tabang kalai lah di pacik lapeh juo di ma bagai tagurajai Taka dinan kareh dia batimbo jalan. Hati nana risau dan bau galau. Oh sayang, nana bak paneh mengandung hujan. Pado menanam yo silo bak lambau. Oh sayang, elok si sawi dan tugakan. Pado menahan hati risau dia kandung. Elok nagari dan tinggalkan. Hari nan sadang patang-patang. Oh sayang, nana bak dendang apa rintang rusuh. Padonyo bansai dan bau pulang. Oh lalai, elok lah rantau dan pajauh.
Labaa, Sarawak pendek panjang labaa, lari lambe kancang labaa, kalang sandek dan bau lala, condong dia dan jaja. I don't wanna back, I wanna to fight, dia salah mai. I don't wanna back, I wanna to fight, dia ndak bansai. I don't wanna back, I wanna to fight, sampai dan tamai. I don't wanna back, I wanna to fight, dunia akhirat. Hujan namai di kampung surang indah dan kadua, pada bansai dan bawa pulang dia rantau dan pajawah. Kuaikan hati pai bajalan madokan labuah, mandekan doang tolong doakan dan nai satio subuah. Gadang cinta kau orang gaib dia dan marantau, pai nyoidik di kampung utang bertambah di rantau. Dia bukui baju dan nara, untung pado dan sakau, sampai panitia selera kalian dan bang guncang rantau.
Yo di maning jauh padila masa. Oh lalai, batang kabeh batimbo jalan. Hati nana risau dan bau galau. Oh sayang, nana bak paneh mengandung hujan. Pado menanam yo silau bak lambau. Oh sayang, elok si sawi dan tugakan. Pado menahan hati risau dia kandung. Elok nagari dan tinggalkan. Hari nan sadang patang-patang. Oh sayang, nambah dendang apa rintang rusuh. Padonyo bansai dan bawa pulang. Oh lalai, elok lah rantau dan pajauh.
tahun denai menunggu, mengharap udah datang meminang, nyatanya kini tiada kabar barito, denailah lare ecu, yodek mananti, denailah lare ecu, yodek mananti.
Maafkan denai, oi adik sayang, bukan muka sui hati mandutoi, dek untung bana alun batu kabah, denai ka pulang baang, denai ka pulang.
Harok cinta basun tiang ame, galak mani di pasan dengan, ya tu kini den harok same, menanti kuda tak kunjung datang.
Laitani ai manyungkin kasih, aromasan diang di palaminan, namun nan mujud nak dapat diraih, basabah di mananti, denai ka pulang, basabah di mananti, denai ka pulang. Mungkin itu ujian cinta, tagu ko adi menunggu denai.
Denai pun indah kama nyarak, sama berjuang kita berjuang.
Semua berjuang, kita berdua. Maafkan denai, oi adik sayang, bukan muka sui hati mandutoi, dek untung bana alun batu kabah, denai ka pulang baang, denai ka pulang.
Harok cinta basun tiang ame, galak mani di pasan dengan, ya tu kini den harok same, menanti kuda tak kunjung datang.
Laitani ai manyungkin kasih, pulang Masa badi nanti Denaika pulang Mungkin iko ujian cinta Tagu ko adi manggu denai
Denai pun indah kamanya sama berjuang kita berjuang
Sama berjuang kita berdua Berakhir sudah impian cinta Tinggallah puing-puingnya Mimpi yang indah tak jadi nyata Terkikis ombak menerpa
Aku yang dulu engkau sayangi Mengapa kau tinggal pergi Oh di manakah janji yang suci Yang katamu tak berbagi
Ku ingin kau mengerti apa yang ku alami Takdir diriku harus melangkah jauh darimu
Andaikan aku boleh bertanya Apakah ada salah diriku Agar ku jauh dari prasangka rasa cemburu
Tiada salah dirimu kasih Salah pada nasibku sendiri Karena tak punya emas permata hantaran cinta
suci yang katamu tak berbagi.
Ku ingin kau mengerti apa yang ku alami. Takdir diriku harus melangkah jauh darimu.
Andaikan aku boleh bertanya, apakah ada salah diriku agar ku jauh dari prasangka rasa cemburu.
Tiada salah dirimu kasih, salah pada nasibku sendiri. Karena tak punya emas permata lantaran cinta.
Saat harimu berasa kelabu, tetap ada yang bikin harimu seru.
Rela aku terima keputusan darimu untuk memilih dirinya dan meninggalkan aku dalam semak menduri, tergores dan terberi sakit terucap lirik.
Memang aku akui akulah yang bersalah, telah memberi hati walau sekerat rasa. Maafkan aku atas khilafku permainkan hatimu. Mengapa kau dan aku bersua
JID 99 Beauty and Style.
Maafkan denai, oi adik sayang, lalamu denai di rantau urang. Sabalah adik, sabalah sayang, denai ka pulang karana minang. Sabalah adik, sabalah sayang, denai ka pulang karana minang.
Oi udah sayang, usahlah bimbang, denai mana nanti di ranah Minang. Pulanglah udah, pulanglah sayang, capiklah denai, gungguanglah tabang. Pulanglah udah, pulanglah sayang, capiklah denai, gungguanglah tabang.
Tinggi-tinggi tabangnya bangang, baliknya kaku bangan juo.
Oi udah sayang, usahlah gamang, rampungkan badan di ranah Minang.
Usah risaukan udah di Subarang, nantikan udah jo hati tanang.
Baliklah udah karanah Minang, sabalun denai disuntiang urang. Baliklah udah karanah Minang, sabalun denai disuntiang urang.
Maafkan denai, oi adik sayang, lalamu denai di rantau urang. Sabalah adik, sabalah sayang, denai ka pulang karana minang. Sabalah adik, sabalah sayang, denai ka pulang karana minang.
Oi udah sayang, usahlah bimbang, denai mana nanti di ranah Minang. Pulanglah udah, pulanglah sayang, capiklah denai, gungguanglah tabang. Pulanglah udah, pulanglah sayang, capiklah denai, gungguanglah tabang.
Tinggi-tinggi tabangnya bangang, baliknya kaku bangan juo.
Oi udah sayang, usahlah gamang, rampungkan badan di ranah Minang.
Usah risaukan udah di Subarang, nantikan udah jo hati tanang.
Baliklah udah karanah Minang, sabalun denai disuntiang urang. Baliklah udah karanah Minang, sabalun denai disuntiang urang.
Usah risaukan udah di Subarang, kan udah jo hati tanang.
Baliklah udah karanah Minang, sabalun denai disumpeng urang. Baliklah udah karanah Minang, sabalun denai disumpeng urang.
Di ujung jari nanta susun, kasimpan haro di bari ampun. Ayah kandung ampunkanlah kehilangan, denailah kehilangan, urang nan mambimbing jalan, sarato arah padoman. Rembulan malam berbalut sepi, suasana dingin merayu hati. Cahaya di bulan ikut menghiasi, nuansa misteri menyelimuti. Hilang pandangan di dalam mata, bayanganmu menepi di angkasa. Entah berapa lama kau di sana, sehingga diriku ingin bersunyi. Korbankan diri dalam ilusi, hilangkan rindu yang membelenggu, membuang waktu bersama mimpi, walaupun sepi takkan berlalu. Pada malam ku titipkan salam untuk dirimu yang aku sayang. Semoga cinta kita kan abadi, sampai matiku akan menanti. Hilang pandangan di dalam mata, bayanganmu menepi di angkasa. Entah berapa lama kau di sana, sehingga diriku ingin bersunyi. Korbankan diri dalam ilusi, hilangkan rindu yang membelenggu, membuang waktu bersama mimpi, walaupun sepi takkan berlalu. Pada malam ku titipkan salam untuk dirimu yang aku korbankan diri dalam ilusi, hilangkan rindu yang membelenggu, membuang waktu bersama mimpi, walaupun sepi takkan berlalu. Salam untuk dirimu yang aku sayang, semua cinta kita kan abadi, sampai matiku akan menanti. Perjalanan ku rasa kerinduan mencari bayangan, ku kehilangan berkali salahmu selalu aku maafkan, bertahun sanggup ku pertahankan. Kemana hilang sumpah janji setia, tak pernah ku menyangka engkau berubah. Kau pergi di saat ku sayang-sayang padamu, tak mampu suaraku menahanmu. Mengapa cinta engkau tinggalkan padaku yang hanyalah seorang seniman? Mengapa baru kini kau banding-bandingkan dia dengan diriku? Tak mungkin lagi kita bersama, kan seperti dahulu bercerita. Kau pandai berdusta dan seakan aku yang bersalah. Sumpah yang mana lagi kau dustakan, janji yang mana lagi kau berikan. Benarlah kata orang, di keramaian ku rasa kesunyian. dusta dan seakan aku yang bersalah. Sumpah yang mana lagi kau dustakan, janji yang mana lagi kau berikan. Benarlah kata orang, di keramaian ku rasa kesunyian. Benarlah kata orang, di keramaian ku rasa kesunyian.
Rasa ini sudah tak bisa ditahan, rindu ini tak mau lagi bersabar, memaksa untuk segera bersua dengan engkau yang jauh di sana. Andai bisa diriku menjadi angin, ku sampaikan semua keluh rasa ini tanpa ada suatu perantara, agar kau pahami segalanya.
Universitas Negeri Padang berdiri sejak tahun 1954 dengan nama PTPG Batu Sangkar. Visi Universitas Negeri Padang menjadi universitas bermartabat dan bereputasi internasional.
Assalamualaikum warahmatullahi wabarakatuh. Saya Profesor Ganefri PhD, Rektor Universitas Negeri Padang. Selamat datang di Universitas Negeri Padang. Perkembangan teknologi dan tuntutan dunia kerja, dunia usaha saat ini memacu Universitas Negeri Padang untuk mengembangkan diri secara berkelanjutan. Universitas Negeri Padang fokus melaksanakan pendidikan dan pengajaran yang bermutu, riset dan publikasi yang berkualitas, serta pengabdian masyarakat yang bermanfaat.
Universitas Negeri Padang memiliki 8 fakultas. Fakultas Ilmu Pendidikan, 8 program studi terakreditasi A. Fakultas Bahasa dan Seni, 6 program studi terakreditasi A. Fakultas Ilmu Sosial, 5 program studi terakreditasi A. Fakultas Ekonomi, 9 program studi terakreditasi A. Fakultas Pariwisata dan Perhotelan, 3 program studi terakreditasi A. Fakultas Teknik, 5 program studi terakreditasi A. Fakultas MIPA, 7 program studi terakreditasi A. Fakultas Ilmu Keolahragaan, 3 program studi terakreditasi A. Dan Pasca Sarjana, 2 program studi terakreditasi A. Selain itu, 8 program studi mendapat sertifikasi internasional dan 16 program studi dalam proses akreditasi internasional. Kampus Universitas Negeri Padang tersebar di 7 titik di Provinsi Sumatera Barat. Universitas Negeri Padang memiliki fasilitas dan infrastruktur yang lengkap, seperti perpustakaan pusat dengan layanan digital, auditorium berkapasitas lebih dari 8.000 kursi, kolam renang dan lapangan olahraga terstandar nasional dan internasional, serta sekolah laboratorium mulai dari TK sampai SMA.
Hello everyone, nama saya Maria Adeline Buroin. I'm from Capiz State University, Philippines. It's worth to remember and worth to share to the world. Mabuhay UNP!
Fasilitas lain adalah klinik, asrama mahasiswa internasional, hotel UNP, pusat bisnis, masjid, dan pusat pendidikan guru.
We are studying in different faculties at UNP and we are very proud to be international students here at UNP.
We love UNP!
Dalam rangka meningkatkan kualitas lulusan dan menuju universitas berkelas internasional, UNP memiliki laboratorium yang lengkap, didukung dengan peralatan canggih, pusat pengembangan soft skill dan kreativitas mahasiswa, serta fasilitas praktikum dan latihan yang memadai. Kampus Universitas Negeri Padang juga menyediakan fasilitas bagi mahasiswa disabilitas. Capaian terbaik Universitas Negeri Padang. Universitas Negeri Padang meraih peringkat 5 nasional kategori riset dan publikasi di Indonesia. Satuan kerja terbaik dalam pengelolaan barang milik negara. Terbaik 3 tingkat nasional pengelolaan media sosial. Juara 1 perguruan tinggi negeri menuju informatif di Indonesia. Rektor Universitas Negeri Padang meraih Achievement Motivation Person dari Komisi Informasi Sumatera Barat. 10 besar perguruan tinggi terbaik dalam pendampingan desa wisata di Indonesia. Mahasiswa UNP menjadi juara pada MTQ Nasional ke-28. Universitas Negeri Padang juga meraih penghargaan sebagai Badan Publik Informatif dari Komisi Informasi Pusat tahun 2019. Universitas Negeri Padang juga meraih penghargaan pertama keterbukaan informasi publik dari Komisi Informasi Sumatera Barat. Rektor Universitas Negeri Padang dinobatkan untuk meraih penghargaan Achievement Motivation Person tahun 2019. Capaian UNP berikutnya, juara 1 penjaminan mutu tingkat nasional. Terbaik 2 pelayanan melalui internet PTN BLU Satker se-Indonesia. Peringkat pertama keterbukaan informasi publik tingkat Sumatera Barat. Pengelola aset terbaik di antara 720 Satker wilayah KPKNL Padang. Universitas Negeri Padang juga meraih penghargaan 1 PTN BLU dalam program kegiatan dan anggaran tahun 2018 tingkat nasional. Mahasiswa UNP menjadi terbaik 1 pada Festival Tari Nasional. Juara 1 kontes robot tingkat regional 1 Sumatera. Juara 2 kontes mobil hemat energi dan pendatang baru terbaik. UNP juga mendapatkan penghargaan dari Kemristek Dikti sebagai penyelenggara kontes mobil hemat energi terbaik. Prestasi berikutnya, juara 1 kompetisi pariwisata Indonesia kategori Tourism Advertising Video. Mahasiswa UNP meraih medali cabang renang dalam Pekan Olahraga Mahasiswa Nasional. Peringkat 3 MTQ Mahasiswa Nasional. Juara 1 Lomba Debat Kritis se-Sumatera. Juara 2 Lomba Karya Tulis Ilmiah Nasional. UNP juga sukses menjadi pelaksana event nasional dan internasional. Universitas Negeri Padang tumbuh dan berkembang dengan moto Alam Takambang Jadi Guru.
Dan Assalamualaikum warahmatullahi wabarakatuh. Hello there. My name is Anissa Upa. I'm one of the alumnus from Universitas University, especially physics department. It's been almost 2 years since I got graduated in December 2019. Now I'm working in one of the biggest startup companies in Indonesia. Even in Southeast Asia, we focus on education, called Lualu as field education consultant. In my job right now, we face problems. We usually sit together, talking what we do, having conversations about fundamental things, and trying to get set frequency to have the best result of solutions. So when you have a question like, what is the relation between your job and my manager in university? I think this question reminded me when I was a student in physics department. We learned that the definition of physics. I think the way of thinking in physics is so related. So I think the main point of my job as my manager at university is the mindset that I think that's all for me. See you next time. Bye-bye.
Universitas Negeri Padang, established in 1954 with the name PTPG Batu Sangkar, UNP Vision, becoming a reputable, internationally recognized university.
Assalamualaikum warahmatullahi wabarakatuh. I am Professor Negeri PhD, Director of Universitas Negeri Padang. Welcome to Universitas Negeri Padang.
UNP has 8 faculties and 1 postgraduate program. Study programs has 8 full study programs certified by UNP, 2 international classes, and 1 dual degree program. Universitas Negeri Padang has the best quality facilities such as Sports Science Center, Library, Student Support Center, Laboratories, Micro-Teaching Center, IT Center, Career Development Center, International Service, Polyclinic, Muscu, Business Center, and International Student Dormitories.
Hi, my name is Farhan. And I'm Hibzi Liman. And we are students from Republic Polytechnic in Singapore.
Kami akan membawa ilmu dari Universitas Negeri Padang ini ke Papua untuk membangun Papua lebih baik.
We are studying in different faculties at UNP, and we are very proud to be an international students here at UNP.
We love UNP!
The impact of technology and the industry nowadays have triggered Universitas Negeri Padang to develop sustainable programs. Universitas Negeri Padang focuses on education and qualified teaching process, research and high-quality publication, then community services that give advantages to the society.
Selain akreditasi dan juga fasilitas yang memadai, Universitas Negeri Padang juga mempersiapkan mahasiswanya untuk dapat bersaing di dunia pekerjaan termasuk di dunia internasional.
The best achievement of Universitas Negeri Padang in the last 4 years. The best university in programs, activities, and budget in Indonesia. Receive an award as the organizer of an energy efficient car contest in Indonesia. University with the best asset management. UNP is the best university with quality assurance in Indonesia. The second best university with information services via internet in Indonesia. UNP also won an award as an informative university and the first winner in the public information disclosure. Universitas Negeri Padang is the best tourism village companion university in Indonesia and the third best information manager through social media. At the end of 2020, the rector of UNP was awarded the Achievement Motivation Person Award. The students of UNP contribute and excel at the national and international levels in order to internationalize and produce graduates with global competitiveness. UNP is following international accreditation and certification such as ASIN, ACAS, and ASEAN University Network Quality Assurance, AUNQA.
Bapak.
Zoom dia kak. Zoom dia kak. Mana kak? Zoom dia.
Ngomong aku tập duyên.
Ini video doa tuh. Udah on kamera kak ini.
Iya, on kamera kak. Tadi emang kak.
Kami berkumpul untuk maju, jiwa bersatu dan tekad. Kami berkumpul untuk maju, jiwa bersatu dan tekad demi tujuan yang mulia, kembangkan ilmu-ilmu fisika. Junjunglah tridharma kampus kita, tunaikan kewajiban sivitasnya agar tercapai cita-cita, mengabdi pada nusa dan bangsa. Fisika warisan ilmu eksakta, fisika dalam panji biru FMIPA. Tunjukkan sikapmu, tunjukkan karyamu, bersatu dalam hati, senada dalam jiwa fisika.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Alright, selamat siang Bapak dan Ibu. Kita akan melanjutkan sesi kita pada sesi selanjutnya. Tadi sudah kita breakout maksud saya, ke masing-masing room. Hari ini kita akan kembali di satu room utama bersama. Namun tentunya room kali ini kita akan bergabung dengan pemateri kita yang ketiga, 4, dan 5. Ladies and gentlemen, thank you so much for your cooperation. We still on this seminar and of course international conference. We are already going to the breakout on each one of the room, start the room 1 until the room 10. But right now we continue this event, and of course this business going to the next keynote speaker. And keynote speaker is coming up. It's already joined with us on this application on Zoom, and he was from France. All right, the Professor Fabien Mieux-Mandré. Is it right? My spell spoke that name?
Yes, it's okay. Can you hear me?
Fabien, I can hear
Yes,
you.
can you hear
Sorry,
me?
wait a minute. Prof. Fabien?
Yes, can you hear me? I hear you.
Prof. Fabien?
You don't hear me?
No?
Yes, we can hear you, Fabian.
Oh, wait a minute.
We can hear you. We can hear you.
Okay.
Clearly.
Prof. Fabien?
I hear you very well.
Yeah.
Is it
You
okay on
too.
your side?
Me too. Okay.
Prof. Fabien?
Okay.
Do you hear me?
Yes, I hear you perfectly well.
Okay, that's a wonderful. The background of education, and right now, Prof. Fabien is a professor at École Normale Supérieure Paris-Saclay. Oh, I'm so sorry, I'm not really good in France. Would you like to teach me how to call your name and your university?
So the name of the school, it's École Normale Supérieure Paris-Saclay.
École Normale Supérieure Paris-Saclay.
Which means Normal Superior School.
Oh, okay, I know that. So what we started this moment with Comment ça va?
Yes, very well.
That's
Thank
wonderful.
you.
Right now, ladies and gentlemen, from the director of the ESM, supramolecular and macromolecular photophysics and photochemistry, we presenting to you, it's a Professor Fabien. Time is yours.
Thank you.
You're
Thank you,
welcome.
Mr. Chairman. And I want to start by thanking the organizers of this symposium to invite me to give this lecture. It's a pleasure for me to be with you, even it's only online and not in presence. So what I'm going to present to you is a research that has been done in our lab. Our lab is devoted more to photophysics and a little bit also to chemistry, synthesis chemistry and electrochemistry. But the topic of my talk will be devoted to functionalization of graphene, and especially inserting metallic nanoparticles inside graphene. And I will explain you our strategy to design these materials, the composites, and also the applications that are mainly targeted to be energy storage and electrocatalysis. So the outline of my talk will be divided into 3 parts. The first part will be devoted to the functionalization of graphene with tetrazines to design nanocomposites for energy storage. The second part will concern the electrodeposition of silver nanoparticles on graphene, and the third part will concern the synthesis of gold nanoclusters and its incorporation also on graphene sheets. So I think everybody knows what is graphene. Graphene is usually represented as a single layer of sp2 carbon. And of course, it had been well known now for more than, let's say, two decades, with a special date, which is 2010, with the awarding of the Nobel Prize for Physics to the inventors, to the discoverers of this pure graphene. which has a lot of advantage, which are acknowledged, like mechanic properties, the high conductivity, and so on. But this is not the graphene we are going to deal with, because actually single layer graphene is difficult to obtain, and it's more the topic of let's say studies as single objects. And as we are chemists, we are more interested in investigating the material and not a single nano object. So if you want to handle material, usually it's more convenient to use what we call functionalized graphene sheets. And functionalized graphene sheets is usually made from graphite, because in the nature, this is the more, let's say, spread form of carbon you can find. And so there is a method which is known for a long time now, which is the Hummus method, which allows, starting from graphite, to obtain graphene oxide in 2 steps. The first step is in an oxidation process, and the second step is exfoliation, which means that the several sheets of oxide graphite will be separated from each other. This is obtained by thermal treatment, and you obtain at the end not graphene but graphene oxide, which means single sheets, but not of all sp2 carbon, but it means that there are a lot of oxygenated function on it. And usually the final step is a reduction step, because you don't want to have all these oxygenated functions. You want to reduce the material. And this is possible by changing the exfoliation temperature, for example, at the end, to obtain a material that we are going to call FGS, functionalized graphene sheet, with a number here after FGS that corresponds to the ratio between carbon and oxygen. So this number will be higher as the oxygenation of graphene will be lower. And typically we are going to deal with FGS 13 and FGS 20, which means that the carbon over oxygen ratio is equal to this number. Okay, so why the high quality graphene, while having very interesting properties, is difficult to handle? It's also expensive to produce. And it has also an intrinsic drawback, let's say, which is the weak catalytic activities because of the its bond gap equal to 0. That's why we want to investigate reduced graphene oxide. So not graphene oxide in itself, because graphene oxide has a major drawback, which is its low conductivity. Also, it can be stabilized as dispersion in several media, but its low conductivity is a real drawback. So reduced graphene oxide has, let's say, a combination of advantages, which is the presence of functions, which allows to derive this function afterwards, and also its conductivity, which is not as high of pure graphene, of course, but which is sufficient, let's say, to use it as an electrode material. That's typically what we are going to use. Anyway, there is also another drawback with reduced graphene oxide. It's the strong interaction between the sheets, because you have hydrophobic interaction, pi-pi interaction, that makes this graphene sheets stick together. And so if you want to handle this as a material, you need to reduce this interaction. And for that, the functionalization will be useful as well. So functionalization of graphene has several purposes. The first one is to handle the material, to reduce the interaction between the sheets. And the second one, of course, is to introduce new functions. That is to use graphene with its advantages, for example, high conductivity and sometimes transparency, but also to add new functions and by adding chemical functions on it. So how to do this? There are many methods. Of course, in the literature you can find to introduce functional graphene. So I will just develop a little bit those that we have investigated in the lab. What we have done is to use tetrazine derivatives, because we know this kind of derivatives. We have investigated them for different purposes. So tetrazine is this aromatic ring here. You have this 4 nitrogen in this aromatic ring. And the main properties you have to know of this molecule, it's its ability to, let's say, it is in its electron affinity. It means that when you put this 4 nitrogen on a, let's say, benzene ring, by substituting carbon by nitrogen, you introduce a strong electron affinity. It means that you can add 1 electron or even 2 electrons on this molecule, and you obtain something which remains stable. Also, the chemistry of these derivatives is interesting, because we can produce the allergenated compounds. So first, you see that there are 2 positions for substitution, because you have this 6 atom ring here, it's 4 nitrogens, and so of course the 4 nitrogen cannot be substituted, but there are 2 carbons here and here that can be substituted. And among the possible substituents, there are halogens, for example here chlorides. And the dichlorotetrazine is a starting compound that we can produce at the gram scale. So we use it as a really starting compound, and we can produce, for example, oxygenated alkyl chains by substitution. And we can also produce aromatic substituents like pyridine here. And we are going to use these 2 kind of derivatives to functionalize graphene. So I won't develop the first example here, which concerns mainly the substitution of oxygenated graphene or graphene oxide using a nucleophilic substitution. And we mainly develop the second chemistry here, which is cycloaddition, which means here this means inverse demand Disalder reaction. So the Disalder reaction is a cycloaddition between a diene, which is here the tetrazine ring, and a dienophile, which is here the graphene. So it means you are going to react 1 double bond here coming from graphene with the 2 double bonds which are conjugated in the tetrazine ring, and they are going to react almost spontaneously. You have to heat a little bit to make a cycle here. From this cycle, you are going to expel N2 molecule, which is a strong driving force of the process, which is going to transform here this ring into a pyridazine ring, and then oxidation will give you at the end this compound. So this reaction is 1 step, just to heat, and you have the final product at the end. So, for example, if you engage this bipyridine tetrazine in a Disalder reaction with graphene, what you're supposed to obtain at the end is a covalent link here between this pyridazine ring and the graphene, and the 2 substituents which were initially here are going to be introduced into graphene. So the basic idea is that you have this aromatic ring here, the tetrazine ring, which is used to graft, to make a covalent link on graphene, and the 2 substituents here that remain intact, that remain the same at the end. So be careful, the drawing is a little bit confusing, because you have the impression here that there is a link. There is no link here. So pyridazine is not directly linked to graphene, only this pyridazine ring here is covalently linked. Okay, so I will show you examples of this functionalization of graphene with tetrazine. First, to design nanocomposite for energy storage. So when we speak about energy storage, what we have in mind is electrochemical storage. So charge storage in electrochemical devices. And what we target is the production of what we call supercapacitors. So what are supercapacitors? They are systems that can store charges and which have intermediate behavior between pure capacitors and batteries. So I remind you that pure capacitors, the basics is based on electrical double layers charging. So it's electrostatics. So usually it's obtained with carbonaceous materials, like porous carbon, for example, are good materials for that. They have the advantage that it's purely electrostatic, so it's pure physics. So it is very fast process. But of course, the amount of charge you can store is limited because there is, no compensation of the charge. So in terms of properties, it means that the energy you can store is very low, but the power is high because the process is fast. Conversely, the opposite, you have batteries. So batteries are made on process which are redox process. So you have chemical transformation. So in that case, when you are going to inject charges, there will be chemical transformation, redox processes that are going to occur. And the advantage is that you can store a much higher amount of energy typically because the charge you are going to inject will be compensated. But of course, as it involves chemical transformation, it's much slower. So the power will be low. So supercapacitors are supposed to be in between. So they are supposed to combine advantages of capacitors and batteries. They will have a higher amount of energy compared to capacitors and higher power compared to batteries. And typical materials to design supercapacitors are either oxides, metal oxides, or conducting polymers. And a pseudocapacitor is a system in which you have a combination of the two effects, means double layer charging, and also the redox process. The two are combined in the property. So our idea is to make a composite between graphene and an electrode material which will be active for supercapacitors, namely a conducting polymer. So this is the scheme summarizing the general idea. We have HES20, which is the highly reduced graphene oxide, which is here represented without any function, which is not the case. In practice, you have some function and some defects from time to time. After sonication, you are going to disperse them in a solvent, and you are going to make them react with the tetrazine derivative with two pyridines. By cycloaddition, you are going to graph the two pyridines. And it means that you're going to change the surface properties of the graphene, and you are going to introduce nitrogen entity function on the graphene sheets. And in the second time, so you are going to separate the sheets, and you are going to introduce functionalities on the sheets. And this will help in the second time to introduce a second material, which is here represented in green, which is polypyrrole. And this will help because you are going to promote some strong interaction between these nitrogen emitting functions you have here and the pyrrole monomer, which have hydrogen on the nitrogen here. And so that is likely to develop a hydrogen bond with this nitrogen emitting function. So this is the idea, so that we can make a true composite in which we hope that the conducting polymer chains will be inserted between the graphene sheets. So the target is to obtain at the end a true composite in which the two materials are really embedded and not separated. The way you are going to incorporate the conducting polymer on this in graphene, we chose electrochemical polymerization. You can do it also chemically. Conducting polymer are produced from monomers by oxidation processes. So you can do this oxidation either chemically or electrochemically. We chose to do it electrochemically. That means that we have to deposit this material on an electrode that will be polarized at a certain potential, so that the polymerization of the pyrrole will start. And we can control with electrochemistry, this is the advantage, we can control the amount of conducting polymer you are going to add at the end. So this is represented here, the cyclic voltammetry, current versus potential. We made it by cycling the potential between two values. And depending on the number of cycles, you are going to tune the amount of polymer you are going to have at the end in graphene. Okay, so we have characterized the material, so I have no time to present all the characterization, but one characterization which is useful is thermogravity analysis. That means you are going to heat the material until it loses weight. You are going to measure the weight loss. And this allows you to evaluate the amount of conducting polymer you have, because the organic conducting polymer will start to decompose first. And so you can see that this decomposition you have is typically proportional to the amount of conducting polymer. So typically this value here is proportional to the amount of conducting polymer. And what interests us at the end is a characterization of the capacitance, which will measure the amount of charge material is going to store, which can be, in the first approximation, obtained by simply scanning the potential and measuring the current. Because here the material is directly obtained, deposited on an electrode. So you can cycle the material by polarizing the electrode between two values of potential and measure the current. It's very simple. So you see the response. FGS20, which is starting material in black. FGS20 BPP is the functionalized graphene with the bipyridine tetrazine, which has almost the same response. And when you introduce the conducting polymer, you see the curves in green and in blue, that the amount of charge is going to be higher, simply because the amount of charge here, you have current versus potential, is measured at the area under the curve. So you have a rectangle form. That means that you have a double layer process mainly. And when you integrate this, so you measure the area, it's directly proportional to the capacitance. So here are the capacitance that you can measure. And you see that incorporating the conducting polymer as expected is going to strongly enhances the value of capacitance. So this is known. This is not our discovery. And what is known as well is that there is of course, polypyrrole here is useful to obtain at the end a high value of pseudo-capacitance, but it has a drawback because usually this is at the detriment of the cyclability, because another properties when you design capacitors, of course, it needs to have a high capacitance, but it needs also to be able to be cycled a large number of times. And usually polypyrrole degrades quite quickly when you start to cycle. Yes, by the way, we have also tested the material in coin cells, which is the true way to use it, because if you want to use it in practice, you have to design the coin cell, which is simply obtained by inserting the materials, two layers of materials between two electrodes. You have a spacer, of course, and an electrolyte in between. And in that case, you are going to measure also the capacitance. And we have measured high values of capacitance this way. You have the comparison, once again, between the functionalized graphene and the composite with polypyrrole. And you see the difference between the two materials in terms of capacitance. And you see that the cyclability is very different, because when you cycle the starting graphene material, you have something which remains mainly constant. So you have very few losses. Whereas with the composite, you see that the high value of capacitance very early starts to decrease. And you have this problem of degradation of the material I was talking about. Anyway, we have compared the stability in various media. And what we have found, which is interesting, is that having previously functionalized the graphene by the tetrazine before making the composite, which is the curve in green, compared to the curve in blue, where the graphene is directly engaged in the polymerization of pyrrole to make the composite, offers real advantages. You see, for example, in acetonitrile here, when you cycle in acetonitrile, that the composite here has better performances compared to this one. So So this is the interest of having preliminarily, let's say, graphed some tetrazine on graphene to make the surface of graphene sheets more compatible with the conducting polymer. And this is actually what you observe in all media, in aqueous solution as well. So the behavior is different in aqueous solution, but you see that the green curve is always above the blue curve, which means that this material is always better than this one. Okay, I move to the second part, which is the deposition of metallic nanoparticles on reduced graphene. So I come back to this functionalized graphene by tetrazine bearing 2 pyridine. So we have this material here, which can be easily deposited on the electrode surface. So we can use it now to insert some metallic nanoparticles. Why? Because we have these 4 nitrogen here, which are in perfect position to try to, let's say, chelate metallic ion, or even it's not chelation, but at least coordination, make a complex. So it means that if you put this material in presence of metallic salt, you have chances to incorporate the metal inside. And to obtain metallic nanoparticles, the only thing you have to do is to reduce the metallic salt to make a reduction step. It can be done electrochemically. Why it's interesting to do it electrochemically? It's simply because you can control, through the potential signal, you can control the size of the particles and the way they are going to grow. So the idea is to use potential pulses, and not simple pulses, but pulses which are a little bit more complicated, where you have a growth pulse, which is very short pulse, from a potential where nothing occurs to a potential where you just start to reduce. So that's the potential here. You measure where the current only starts to flow, just to induce the nucleation process. So just to start the reduction very quickly. And then you apply a longer pulse with potential more negative, which is going to promote the growth. Sorry, that's the opposite. Sorry. First pulse for nucleation and short pulse and a pulse at a higher potential for the growth. Okay, so the largely negative potential will start the reaction and so start the nucleation, and then you come back to a less negative potential to let the particle grow. And the time you are going to apply the potential will more or less control the final size. Okay, and that's actually what we observe. If you compare what happens when you have a growth pulse of 1 second versus one of 60 seconds, you clearly see that the final sizes of the particles very different. Here you can observe the large particles, large spherical particles that are produced on graphene by SEM. With the 1 second pulse, you can hardly see them by SEM, but you can clearly see them by TEM. And you can see that, of course, there is a polydispersity in size. It's not a method to have something which is which leads to the perfect monodisperse sizes of particles. But anyway, you see that they are more or less spherical, and their size is in the range of, let's say, 10 to 20 nanometers. You have bigger ones, of course. Some are made by aggregation of small ones. Okay, so this way you can deposit silver nanoparticles on graphene. What is the purpose? In that case, we have tried to investigate the catalytic properties. As I told you before, intrinsic catalytic properties of graphene are usually rather poor, and we can improve them by inserting another material, namely here metallic nanoparticles. And what we have chosen to investigate as a reaction to catalyze is the reaction of reduction of oxygen, which is, for example, the reaction which is involved in fuel cells based on water reduction. And so in water production, for oxygen reduction and hydrogen oxidation. And in that case, we observe some catalytic effect, especially when you, once again, when you compare the functionalized graphene with the non-functionalized graphene bearing both silver nanoparticles. We see that we have an increase of current, and we see that we have a small positive shift of the reduction potential, which means that there is some catalytic effect. And you see here the response of graphene in nitrogen saturated solution. How to incorporate more silver nanoparticles? We can change the tetrazine precursor. So the first example was with this tetrazine, the bipyridine. But if you change the precursor, for example, by removing one pyridine and substituting by hydrogen, you can have a more efficient cycloaddition and at the end incorporate more silver. This is what we observe. If we compare the results for this compound, which are shown here with the two proportion, the percentage of nitrogen you have at the end of the material is in the range of 1%, and the percentage of silver is in the range of 0.1 to 0.2%. And when you change this starting compound by this one, you see that the percentage of nitrogen increases and the percentage of silver increases as well. So this is simply because this compound is more efficient in the cycloaddition process. And you see that at the end you have more nitrogen. Also in the starting compound here, you have less nitrogen because you have substituted one pyridine by one hydrogen. So you have not one nitrogen less at the beginning in the starting compound. And in the final material, you have more nitrogen anyway, because the reaction is more efficient. So changing the tetrazine derivative can allow you to change a little bit the percentage of metal that you're going to incorporate at the end. And this is visible on the after functionation of graphene. We see that we have higher amount of nitrogen. No, we don't see the higher amount of nitrogen. We see that we have a higher amount of silver nanoparticles. And we also see that they are smaller when using this compound compared to the previous one. Okay, the final properties in terms of electrocatalysis are a little bit disappointing because they are more or less the same. We have an effect because when you compare the starting graphene with the functionalized graphene, you see the shift of the potential in the positive direction, which means that the reaction for reduction is easier, which is what we expect. This is also the case here, but you see that the variation is it's very small actually. Okay, final part of my talk, I will show you how we can incorporate gold nanoparticles and gold nanoclusters in graphene. So what we're talking about here is nanocluster. Nanocluster is defined as something which is intermediate between nanoparticles and molecular chemistry. So typically the range which is concerned is the range, let's say around 1 nanometer. And let's say less than 2 nanometers. And there is a frontier which can be defined between nanoparticles and nanoclusters with noble metals like gold or silver. And this frontier is defined by the absence of plasmonic properties. Okay, so to have plasmonic properties, you need to have a nano object that have a minimal size, because you need to have surface properties which corresponds to nanoparticles and not to molecules. And so this frontier corresponds more or less to 2 nanometers. So one of the main differences between nanoclusters and nanoparticles in terms of gold will be this absence of plasmon bond. So absence of absorption bound in the visible range, which means different optical properties for nanoclusters compared to nanoparticles. And the usual way to design gold nanoparticles or gold nanoclusters is based on the use of thiols, and especially alkyl thiols, for example, dodecan thiols, which are known because thiols are known to stabilize gold through the sulfur gold bond. And typically, the synthesis which is used is to mix the gold salt, a thiol, and a reductant, which can be whatever you want. There are several examples. And if you put a large excess of thiols versus the reductant, you are going to decrease the size. So you can shift this way from gold nanoparticles to gold nanoclusters. So that is the idea we have implemented with tetrazine, because tetrazine are oxidant. So as they are oxidant, they can be reduced, and they can be reduced by thiols. So the idea is to make a reaction between thiol and tetrazine to obtain here the reduced form of tetrazine that will be the reductant for the gold salt to produce the gold particles or the gold clusters. So the idea is to make a one-ton synthesis by mixing the tetrazine, the thiol, and the gold salt in an appropriate solvent, a polar solvent, let's say, and at the end to obtain gold nanoparticles. That was the initial idea. And in fact, we obtain gold nanoclusters depending on the proportion. So this is the result when you mixed the three, the thiol, the gold salt, and the tetrazine. What you observe is a change of color, gradual change of color, and at the end you have something which is yellow. If you do it in absence of gold, you have also at the end something which is pale yellow, but the kinetics is different. So this is what you observe in TEM. So you clearly see these small clusters, which have a size. This is a zoom. You can see you can see them more clearly. So the mean size is around 2 nanometer diameter. So they are at the frontier with the nanoparticles, but actually they are nanoclusters because they don't have plasma bonds. And we have investigated the mechanism, and corresponds to what we expect. Means we start with this tetrazine that reacts with thiol in a redox reaction. So this is reductant, this is oxidant. This compound is reduced. This is here reduced in an anion, but more probably as we are in a polar solvent with protons, this is protonated. So we have here protonation of the nitrogen. And this reduced form of the tetrazine will be the reductant engaged in the reduction of the gold salt to produce the gold zero that is going to produce the gold clusters. And we can prove these mechanisms by observing the changes in the absorption spectra, where we clearly see that the absorption band of this compound disappear, and that we have a growth of band here that corresponds to this reduced form. Okay, we have made XPS to have an idea of what we have at the end in terms of ligand of the gold clusters. Of course, we have thiols, but we were wondering if we have also tetrazine, remaining tetrazines that can be used as a co-ligand with the thiols. And when you look at XPS results, you have the feeling that tetrazine does not play the role of ligand because there are more or less no nitrogen at the end, or very few amount of nitrogen. You have mainly sulfur, which is normal because you have the thiol that stabilize the gold clusters, but you have almost no nitrogen at the end. But this is a little bit, let's say, deceiving, because if you make NMR, you will see that the tetrazine are involved. Just before, we have been able to isolate the clusters from the unreacted molecular compounds by chromatography. You have here the isolation of the clusters. After performing HPLC, you are going to collect a sample that corresponds to pure gold nanocluster. You see the high resolution TEM image of this isolated cluster. And NMR show the evidence that we have.
Prof. Fabian?
Yes, I finished.
That's okay. That's okay. Just continue. We just got to 5 minutes.
Okay, I finished.
Yes.
So you can see that the proton signal of the clusters involve 4 signals that correspond to the 4 protons of the pyridine here, that are a little bit shifted compared to the pure compounds, which is normal because of the interaction with gold. You do not expect to have exactly the same chemical shift and as you have in the starting compound. Of course, you have also the proton of the thiol that you find in the clusters. But more interestingly, with the carbon NMR, we have been able to demonstrate that in the gold clusters, you have 4 signals that correspond to the 4 carbon, which are here on the pyridine ring, the substituent, which are also a little bit shifted compared to the pure compound. But this demonstrates, finally, that on the gold surface of these gold nanoclusters, you have the 2 ligands, the dodecanthiol, and also the tetrazine that is present on the co-ligand. And what we think is that we don't see it in XPS because the tetrazine is a very volatile system, so it can sublime, actually, and as XPS is performed in high vacuum condition, probably the molecule has sublimed, and so it's not present anymore. So that's why you don't see it. But NMR confirms its presence. And finally, we engage these gold clusters in composites with graphene by simply mixing at various conditions of temperature and duration, but by simply mixing the functionalized graphene sheets with the gold nanocluster, and you see that at the end, the TEM image clearly show that you are able to spread this small gold nanocluster on the surface of the graphene sheets. You have only gold nanoclusters where you have graphene, you have no nanocluster outside. And this means this way you have a material which is able to be engaged in, for example, catalysis. And we have performed first attempts with the gold nanoclusters, once again with the oxygen reduction reaction, and you see the effect here. You see once again this shift. This is the peak of reduction of oxygen, which is positively shifted when you use the gold nanocluster as expected, showing the catalytic effect. So I will end at that point by summarizing that tetrazine is one way among others that can be used to functionalize graphene, to introduce new function in graphene that will help to insert a new material, for example, metallic nanoparticles, that can be silver nanoparticles or gold nanoclusters, that these materials can be useful to introduce catalytic properties. And also for energy storage, and we are currently investigating also the possibility to enhance the energy storage properties by designing these bridges here between graphene sheets, bridges that involve redox units, so that you can have at the end a combination of the double layer effect coming from graphene and redox units here that are going to help to store more charges in the final material. And then we end by thanking all the people that took part to this work, the permanent people of the lab here, the PhD, and I will of course mention that most of the work I presented here have been done by Yadi Benarus. And I will thank you for your kind attention. Thank you.
All right, thank you, Professor Fabien. Merci. Next, we just moving faster, going to the chat room because we got 3 questions. Oh no, I mean just 2. So sorry, I catch up. That's both of them. What kind of new properties that you want to get by using resigned derivatives? Oh no, derivative, which are located in between the 2 layers of your graphene. And then the second question is how to fabricate this material which tetrazine in between 2 layers, graphene and not on surface. Is it costly? And then you already explained, but I missed it in detail. Thank you. Merci.
Okay, so you mean at the end, for example, doing that?
Yeah.
I think the question are related to that. So how to incorporate tetrazine in between? So it's simply because we are using 2 kinds of tetrazine. One tetrazine will be engaged in the cycloaddition. So it will be used for covalently graft the graphene. So it will be transformed into a pyridazine ring. So you lose 2 nitrogen. But by using these 2 anchors here, you have 2 anchor groups, but in between you have tetrazine that will remain intact. And so this tetrazine will be able to store 1 electron. You see? So that's a complement what we did with graphene oxide. With graphene oxide, we were able to functionalize graphene oxide by tetrazine, and the tetrazine remains intact in that case because that was nucleophilic substitution, not cycloaddition. But the problem is graphene oxide, as graphene oxide is not conductive enough. So to do it with reduced graphene oxide, where you have less oxygenated function, more carbon, more sp2 carbon, you need to have 2 units. One that will be used to graft, which will be this H tetrazine here, and 1 tetrazine in the middle that remain here just after for the properties, to introduce some redox properties into graphene. That's the idea, and actually we did it. That's the current work of the PhD student, Margareta Bosmi. We have, who have already demonstrated that at the end, we find the redox properties of this tetrazine here in the final material. So we are currently investigating further, for example, by EFM, to see if this structure with these bridges is actually what we have in material. But we are currently doing that. So the idea is that having 2 different tetrazine, which is used to graft through cycloaddition, and that more or less disappeared, it's transformed into pyridazine, but this electron affinity is much less in pyridazine than the original tetrazine, but you have this tetrazine here that remains as such. I hope it answers the question.
Merci. And then next question. How do you choose which molecule you want to use for each application from the chat room? We got that question. How do you choose which molecule you want to use for each application?
How I choose the molecule for each application?
Yeah. You can check out your chat room. The participant asking you about how do you choose which molecule you want to use for each application?
Well, the idea is that we know already from reported studies that some molecules might be active for example, to catalyze some reaction. So here the idea is how we can incorporate this molecular unit, which we know from other studies that it is active, that we can incorporate it into graphene. So graphene will be a support and will bring some electron conductivity and will be support to introduce this active molecule. So usually you don't discover the catalytic properties of a molecular unit. We use something which is already known as being a good catalyst, and we try to incorporate it into graphene at the end. That's the same, for example, to design the nanoparticles. We know that the pyridine tetrazine has a coordination site, has a good coordination site for metals. So, for example, the idea is how we can use that to design material and to have at the end a composite which is the best that we can hope. You see, that's the idea.
Okay, that's a good. Thank you so much. Anyone else? I thought it's already enough. Thank you so much, Professor Fabien from.
Thank you.
Merci. You want to say something to us? You want to say something to us?
Well, I want just to thank you, very much to welcome me in this symposium. I hope that also the agencies may be made of physicists. They have known, they have understood the chemistry I introduced. I hope so. And I wish you a very nice symposium.
Yeah, of course. Actually,
Thank
we
you
are
very
from
much.
Padang State of Universitas Negeri Padang. It's very interesting to open the relationship with your university, with us university, and of course we can make in the future like LOE, letter of understanding, maybe something like that, and we can exchange our students over there and talking about this. And yes, it's all about basics and relationship.
Okay.
So what I call
That's also
merci.
yes.
Yeah, we call that
Merci.
merci. Merci. Merci. Right, thank you so much. Kita let applause on your screen on the Zoom for Professor Fabian. All right.
Thank you.
Applause.
Thank you.
Merci. Right, thank you, Professor Fabian. We gotta move on to the next. Oh yeah, next keynote speaker. It's from Sweden. Wow, so far away, Sweden. And right now I'm in Indonesia. But
yes, hello.
Hello, sir.
Nice to
meet you.
Nice to be there with you.
Very good. Your camera is on, good setting, and I'm so jealous with your camera.
Yeah, so I think everything is in order.
Yeah.
Right.
All right. Before we start with your presentation, but let me introduce you again. Everybody knew, but that's officially, ladies and gentlemen, this is Mr. Professor Dr. Rick Smittenberg. Is that right?
Yeah, approximately. That's good enough.
Okay. I know your accent. Oh my God. Smittenberg from Stockholm University from Sweden. And of course, when we're talking about him, and Associate Professor in Isotope Organic Geochemistry, Department of Geological Science and Policy Center of Climate Research, Stockholm University, Sweden. How is that the weather there or there right now? Is that good?
Sorry?
The weather good?
I am actually even in Switzerland at the moment.
Switzerland?
But it's not so far away from it. I go back to Sweden in 2 days. So, yeah.
Okay, I thought you're in Sweden, but right now you're in Switzerland.
Yeah, physically I'm in Switzerland, but my professorship is in Sweden. I go back there in 2 days.
I hope you found
but I'm presenting out of ETH Zurich at the moment, where I collaborate.
Oh, sounds
but
good.
I have also collaborations in Indonesia, and that is why I got invited. So it's a pleasure to
and in the future we hope so we can to make it more relationship and partnership.
Yeah.
All right, here we go. No another, ladies and gentlemen, it's time to move on to Mr. Professor Dr. Rick Smittenberg from Stockholm University on Sweden.
Yes, so let me share the screen here. I think you can see this, I assume. Let me know if you cannot. Then, so we're shifting gears quite a little bit from the more physical part, and of course, and I am talking about paleoclimate, so past climate. So we all know current climate change, but how do we know that it's actually changing? We only know it from looking at the past. So that is my main goal of my research, and I am using actually molecules to do that from sedimentary records. And then a big focus of my research has been and still is, I somehow landed into that the tropical Asian Pacific realm. So that is also how the collaborations came to be out of my interest. So it is actually a bit of an overview of research of the last 20 years with many collaborators from different universities I have been affiliated with and so on, including Hamdi Rifai now at there, and Caroline Bouvet de Massenev, who is also presenting at this conference. It's actually via her that this contact got to be. So I have to thank you there. There's been funding, of course, from different sources. But let me introduce you a little bit to the topic. Now I need to move forward somehow. Yes, okay. So I will introduce about tropical Asian Pacific climate in general. Of course, you live there, so you know it maybe better than I do, but more from a paleoclimate perspective. And then I talk about how you can use molecules and their isotope composition to trace back climate. And then I have 2 case studies doing so. So the tropics, they actually cover half of the globe surface, and they play a large role in global climate because this is where, of course, most of the heat, the solar heat comes, and from there it needs to get distributed to the higher latitudes. And that, of course, goes via the climate system, which has trade winds across the or north and south of the equator, and then further higher latitudes is westerlies and so on. A critical thing is that paleoclimate research has been very common in Europe and North America, but much less so in the tropical realm. So there's actually much less information from the tropics compared to higher latitudes, even though it's equally, if not more important for the climate system. What you see on the right here is actually the total annual rainfall. And here I introduce one part of the climate system that we have, which is the intertropical convergence zone. So this is where the trade winds come together, and then you get some deep convection there where a lot of energy and humidity is shot up high in the atmosphere, and then from there actually gets exported to the north. And this connects with the monsoon systems in Southeast Asia and Australia. So this is another picture of that, and actually a moving picture where you see the precipitation over the years going from winter to summer, or your wet and dry seasons, essentially, even though you have where you live, it's always wet, except during El Niños, when these kind of climate systems move, because you can also have big convective cells here, which really are very active above this very warm tropical water called the Indo-Pacific Warm Pool. Maybe I change my pointer to a red pointer now. So yeah, now you can see the laser pointer better. So it's defined as sea surface temperature higher than 28 degrees, and you get really strong convection with a lot of export of heat and humidity, latent heat, to the higher altitudes and latitudes. But this tropical rain belt and these convective cells, they may change through time. And how has it changed through time? And how do we find out about that? Now I need to, yes. So the research question is, how has tropical hydroclimate actually varied? And if you see changes, what are then the driving mechanisms? There you need to connect with climate models to understand the physics behind it. Over the last, well, maybe 50,000 years, the last glacial versus the current Holocene warm period, and has it been shifting north, south, east, west? Has it been stronger or weaker? And maybe it has even influenced human societies over the ages. So the way to go about it is you have climate models that try to understand or really model how climate behaves, but they need to get informed by paleoclimate records. And that is what I busy myself with. So they can validate if the climate models actually tell the truth or not. So how do I do that? I actually look at molecules, at organic molecules. Go to any place on Earth, there is vegetation, there are bacteria, there are algae in a lake, there are peatlands, there are forests, etc. But if you can then go on to the molecular level, you get, of course, organic molecules. And a large part is actually cell wall material. But not only that, of course, there is also helper molecules in the cell walls, and of course there's thousands and thousands of different organic molecules made by life. And they're not all the same. They're all different, of course. So, and the nice thing about that, this large variety of molecules, you can link them to different types of plants or different types of organisms. So for instance, you have these 3 kingdoms of life, in a way based on their genetic diversity. So here you have the genetic tree of life. So the longer this distance is between 2 ends, so this is here animals, if we would zoom in here, we would have humans here as well, but we are fairly closely related to all kinds of plants, and much further related with archaea, which is like very small microorganisms. Again, different from bacteria. And they all make different types of molecules, and some can be very specific. And then you can call it a molecular fossil. And then, of course, some of these molecular fossils get preserved, just like you have oil reservoirs. That is essentially organic matter preserved for a long time and a large amount together. Those are essentially the basis for oil and coal reserves. But not only there, they also just get preserved in a lake or an ocean floor, etc. So if you then look at this organic matter that has been buried through time, you can look at their molecular fossils. And then if you see changes through time, and maybe it got wetter or drier, or the vegetation changed, you can see the changes in the molecules, and with that you can reconstruct past environment and climate. So you can take a sediment core, you go back to time, analyze each slice essentially, and then you can reconstruct the past climate. So a second interesting aspect of it is that you can look at the isotopes. So the stable isotope composition, you will have carbon isotopes. Normal carbon is 6 protons and 6 neutrons. And you have stable carbon, which has 6 protons, otherwise it would not be carbon, and 7 neutrons. But you also have the hydrogen isotopes, and hydrogen is essentially 1 proton, but if you have a proton and a neutron, then you have deuterium. And if that is, of course, part of the water cycle, and if you have water with regular 2 protons, or you have water with heavy oxygen or heavy hydrogen, so deuterium, you have heavy water. And that where that heavy or light water ends up in the water cycle relates to convection and evaporation and precipitation. So they will distill one isotope over the other depending on the process. So now So preferentially light water with the lighter isotopes get evaporated, and preferentially the heavy ones get precipitated as rain in a lake. And then this water is used, of course, for photosynthesis. And now my mouse is not for photosynthesis, and taken up by algal molecules or by plants. And then you can make again this record. So you look at the molecules derived from plants and algae, and look at their hydrogen isotope composition, and then you can reconstruct something about the past rainfall. So the past hydrological cycle. So if there's little deuterium, it typically means it was more wet. And if there's much deuterium in a lake, there's actually residual heavy water, essentially, then there was dry circumstances. So that is the approach that I use. Now I'm trying to click through. Yeah, now it worked again. So, and this picture shows essentially the same thing again. You can relate the delta D. The delta D is the change, the relative amount of deuterium in a sample, so an organic molecule, compared to the standard. So that we call the delta notation. which is easier than the actual ratio measuring. So it's essentially a comparison with a standard. It can be heavy or it can be light. And then precipitation, delta D is influenced by the source, where it comes from, how long that rainfall, that moisture has traveled, and already, so if a cloud is already empty or not yet so empty, essentially, and if it has already moved over land or picked up new moisture over the ocean. So there's a couple of factors that influence the delta D, and that is picked up by leaf waxes from plants, like shiny surfaces on plants. Those are essentially waxy coatings to protect the plants against the weather and environment. And they have picked up this isotope composition. And different plants make somewhat different waxes. And then there can also be microbial lipids and algae. And then you take a sediment sample record out of that. Another useful method that has been developed over the last years is actually try to reconstruct temperature out of molecular fossils. So there's a certain types of bacteria, and they make cell membranes using these kind of structures. So cell membranes are long apolar central molecules connected with a polar glycerols at the ends, and then you get these large molecules called glycerol tetraether glycerol tetraethers, and they have actually methyl branches. And when it's cold, they make more of these methyl branches, and when it's warm, they make less of them. And so by measuring the ratio between the ones with more methyl branches compared to less methyl branches, you can reconstruct past temperatures from the areas where these bacteria live, and they live in peatlands and lakes. So that is a very useful new way of reconstructing past temperatures. They also respond to acidity and maybe some other environmental factors, but temperature is really the strongest factor. Click, my clicking through is slow. So we not only reconstruct past precipitation using the hydrogen isotopes, we also can reconstruct past temperature from a certain lake. And this is called the branched GDGT temperature proxy. And we reconstruct with leaf waxes the past rainfall intensity. And here you can see on the side, this is the isotope composition of rainfall compared to the amount of rain. So here you can see a proof that the wetter it is, the more negative your hydrogen isotope ratio is. So the less of the heavy hydrogen is in your rainfall. So if you then can find back in your molecules the hydrogen isotope composition, you can read essentially back how wet or how dry it was. Click, and keep on having, yeah. And of course, in a sediment record, you can also look at charcoal. If it has been burning a lot, you will find evidence for that, which is, of course, a climate indicator. And I also use there's different types of plants that, depending on the environment, you have C3 and C4 plants. They have a carbon isotope signal. I will not talk about that at this presentation. Further. So that is the way I do things. And now I talk about two case studies. So one is about the intertropical convergence zone in the Pacific, having sediments from lakes in Palau here in the West Pacific, from lakes on Christmas Island, and which is a big coral atoll in the center of the Pacific. Here is Hawaii, and then Washington Island, which is a bit further north. And there was also a lake in that coral atoll. And then here's the Galapagos. That is one case study. A second case study is more near to you. So this is southern Thailand. There's an 80,000 year lake rock record that I present, and some newer results actually from Lake di Atas here in West Sumatra. So this Pacific intertropical convergence zone work, that was already 15 years ago that I started to do that with my then advisor Julian Sachs and colleague, postdocs and collaborators. So I first have this lake in Palau, where you have these rock islands. This is carbonate rocks with lakes in them. And then in these lakes, we have sediment cores. And then I will skip that. In Palau, you can see clearly a link between the hydrogen isotope composition, delta D, and precipitation, just as I showed before. So when it's wet, you get more negative values, and when it's dry, you get more positive hydrogen isotope values. And then you can pick up El Nino years. And this is a reconstruction then of the last 500 years using an algal molecular fossil and its hydrogen isotope composition. So you can see the numbers are much more negative compared to the rainfall, and that is because when organisms take up or use water and they fractionate further against the heavy isotope. So isotopically speaking, we are all lighter than what we eat. And that includes then also water and CO2. So, but still the relative change you can clearly see here. This is the present day or the last 100 years. But then a couple of centuries ago, it was actually much more dry in Palau, which is now considered the tropical wet conditions, but it was clearly drier. And our first interpretation was that it might have been changes in El Nino. But it's also possible, if you go back to this picture of the intertropical convergence zone here, that the whole intertropical convergence zone moved further south or further north because of global climate systematics. A second note on this work is Christmas Island. So this is Christmas Island at 2 degrees north, coral atolls filled with hypersaline lakes. So you get salt water, they evaporate, and then you get these bacterial mats growing in these lakes. But if you go at 4 degrees north, it's very wet. And that is here, the intertropical convergence zone is always above your head, while at Christmas Island, it is typically just north. And so these are two very different climates at very close distance to each other. And what we found here is taking a lake record from Christmas Island is that, so this is on Washington Island, this northern lake where it's really wet. There's a freshwater lake. If you go further down, you find exactly these microbial mats, a characteristic for very dry conditions. So then we know about a couple of 100 years ago, it was actually much drier, even though it was now really wet. So that's more information about changes in climate here. A last note is Galapagos. So this is at 800 meters above sea level. It's a volcanic crater lake on top of one of the Galapagos Islands. And here you can see coring platforms where we take lake cores. And then after all the work of slicing it up and doing dating, etc., you get this another record of hydrogen isotopes, in this case from algal lipids. So here we have Galapagos, and this goes back to 800 AD or Common Era. And it was quite wet here in this middle, in this time of the Little Ice Age, called the Little Ice Age, between 1400 and 1800, when at least in Europe it was much more cold than it was today. And Palau was actually more dry. and in Christmas Island and Washington Island, it was actually also dry. And in this way, we could reconstruct that over the entire Pacific, the mean position, the mean latitude of the intertropical virgin zone was actually further south, and it moved north. So that's a global climate reconstruction of this, important border between the northern and the southern hemisphere, and it has to do with the heat transport between the latitudes and the global climate. The second thing is more close to you, in the Indo-Pacific warm pool, which is here. So normally speaking, you have a lot of rainfall and a lot of convection above the Indo-Pacific warm pool, exporting a lot of heat. But of course, you also have El Niños with all the fires related to it. And it's actually a big feedback also on the global CO2. So the CO2 growth rate per year is actually matches the El Niño. So there's a lot of carbon coming out of the Southeast Asian regions affected by El Niño and climate change. And during El Niños, what happens is that this large amount of convection above the warm pool moves to the Central Pacific. And this whole convection cell turns around, you get downward movement of and dry conditions in your region. So, and the question is, how has this carbon dense, because you have lots of tropical forests and peats, how has it changed through time, and what are the effects on the connections with the global climate? So if we go really far back in time, 20,000 years ago, Indonesia was actually much larger, or whatever it's called now, Indonesia at least, because it was all this what is now shallow seas. It was all land, because the sea level was much lower because of much bigger ice sheets on the poles. But then the climate warmed after the last ice age, and then the sea level rose, and this whole region got inundated and got swallowed by the oceans. So there's been a big change, both in, of course, there were tropical forests, and now it's all gone. And of course, now you have warm waters, and before it was just land, which can be dry. So that must have had quite a large impact. And then there's this record from southern Thailand, which is very well dated with 59 radiocarbon dates. So we have a very good age control of our sediment core. So that is up here at about 8 degrees north. And then here we have a reconstruction. So this is time 20,000 years ago. This is at the present. And we can see that it was clearly much drier during the last glacial period, and then it got quickly quite more wet, about 14,000 years, and then it went down a little bit. This is the younger dryas period, which is the last known pretty cold conditions before the current warm period, the Holocene. And then this is the reconstructed temperature, which follows more or less the same thing. So you can see it was clearly colder, only like 24 degrees mean annual temperatures. And it went up to like 29. And about 100 years ago, it was maybe, 27.5. So it's actually been cooling over the last couple of thousand years in the region. So this is called the mid-Holocene warm period or climate optimum, in fact. And we can actually relate this to solar insolation. So how much solar power arrives at your site, at your surface. So and then this actually connects also when the monsoon system is at its strongest. So in after the summer, early autumn, when the monsoon is actually strongest, in southern Thailand. And when then the sun is also on its strongest, so you see here you have these dotted lines, which is your solar power, in these months, really generates most wet conditions and warmest conditions. And this has actually been going down over the last thousands of years. So the monsoon and the intensity of the convection has gone down because the sun has essentially started to shine a little bit less strong at this time of year. It will have been stronger at winter time. So there's a slow change in solar insolation, making the seasons stronger or less strong over thousands of years. Here below you have another record from Borneo. It's oxygen isotopes from a speleothem, from a cave carbonate deposit. And that actually also follows this solar insolation curve very nicely. So how wet it is clearly linked to how strong the sun or how much energy is actually arriving at the surface. And of course, if we now add CO2 to the atmosphere and we get more radiation out from above our heads down to Earth again, that adds on to the solar power. So we can expect that it actually gets warmer, but the hydrological activity, the hydrological cycle is also clearly increasing. That is what we've seen over the last years, developing ever stronger, unfortunately. But you can see it also back thousands of years, just looking at the solar insolation. So to summarize this, in the last glacial period, the cold long period, thousands of years ago, we actually did have not so much convection because it was dry, and we actually had also cold winter monsoons. Then it started to be more wet because the sea level was rising. It got all much more in a tropical wetland. There were still cold, dry winter airs because there was still quite cold at the end of the last ice age. But we also already started to get really a development of deep convection, of wet conditions, at least in certain seasons, in a wet season. And then over the Holocene, more the typical current climate developed. Then a last thing is Lake de Atas, which is at 1,500 meters above sea level here in Western Sumatra. My PhD student, Petter Helberg, has been working on that, and it's a course also in collaboration with Caroline Bouvet de Massenève and Rifai Hamdi, who have been involved in this record. And here you can actually see also that it was land 20,000 years ago, and then it got actually inundated over the past. And this is all, these circles are all records from other people saying it was drier or wetter at 12,000 years as a reference age. So some results, and then this is for the last 1,500 years, no, not 1,500 years, last 11,000 years. So these are measurements made here in ATA Zurich, where I am actually at the moment presenting the hydrogen isotopes of leaf waxes, where we can see this mid-Holocene, about 4,000, 5,000 years ago. It was much more humid. It was also actually much warmer based on the temperature record. And we can actually relate this also. This is titanium counts from this record. And when there's almost no titanium counts, then there's not much erosion. And if there's more titanium, you have more erosion from the side, meaning it was stronger torrential rains that were active. So in this way, we can reconstruct the climate also for Western Sumatra from this lake record, and connect it or compare it with other records from the region. So this is a compilation of monsoon strength we go back through time. This is 11,000 years ago. This is present, and this is the East Asian winter monsoon and the East Asian summer monsoon strength. And you can clearly see there's a relation between the temperature in Western Sumatra. It was warmer when the monsoons were also stronger, and it was wetter. So the whole climate system was much more active during this mid-Holocene again. And then it waned, it went lower until a couple of thousand years, and it actually been the last 100 years actually unusual if you look closer. This is from Galapagos record. It's a similar record as I presented in my earlier example. It's the frequency of El Nino, and you can even see that the El Nino was much less common at this mid-Holocene warm period, and most likely because the convective cells above the Indo-Pacific warm pool were so strong that it could essentially hold at bay this change in this turnaround in convective cell and Walker circulation. So that is then the end of my talk. Main conclusions: the hydrogen isotope composition of these waxes, they can trace the rainfall amount and the convective strength, and that's a very useful method that I apply. We found that it was about 5 degrees lower temperatures in the Indo-Pacific warm pool area in Sundaland, and that matches other people's information. That it was land before and then got inundated upon sea level rise was very defining for the Indo-Pacific warm pool climate over the thousands of years. And then the correlation or the working together of insolation strength, the solar power, together with the monsoon dynamics, actually dictate temperature and convective activity, causing essentially a stronger mid-Holocene climate, hydroclimate activity in the Pacific warm pool. And there's also a strong connection between the West Sumatra climate, El Niños, and the Southeast Asian monsoon strength. So they are clearly very connected, and we base that also on new lake records from the ATAS. So that is what I wanted to say. I hope that it was clear. Of course, for most of you, this is not your normal thing to do. But yeah, let me know if there's any questions. Thank you for your attention.
All right. We got to move on to the question and answer season. And then here we go. Like to check out our chat room.
Okay, I have the messages here also.
Wait a minute. You want to answer? Prof. Rick?
So I think Caroline has posed a question by the looks of it.
Yeah.
Yeah.
Just go there.
More torrential rains with lower monsoon intensity. Well, it definitely also has to do with it's not only monsoon intensity, it's also the El Nino. So I think how seasonal your climate is. So if you get dry periods every now and then, like an El Nino, then you dry your system out, and then it's much more prone to erosion afterwards when it then suddenly starts to rain heavy. So the rainfall, when it falls, may be equally heavy or even heavier, but the tricky thing is that you also have drying out phases, and then you get more erosion and gully erosion. So that's the explanation.
All right. Next question is from our lecturer, Mr. Hamdi Rifai. question. Sometime we found that the sediment got turbulent. We know it from the age. How to correction our data so that we get the information squarely?
I didn't quite understand the question. I don't see it on my chat, in fact, so.
Chat room, you can check out on your chat room, please.
Yeah, I have my chat room. I only see the question that Caroline.
Wait a minute.
Oh, no, it was before. Okay, sorry, it was yeah. Sediment got turbulences. How to correct our data so that we can so that the sediment is turned upside down, essentially. That's what I understand. Yeah, and then if that's the case, then it's not good. Simply speaking. So of course, if you have an age for 14C and you have your molecular information, then you know it was from that time, of course. But it becomes very tricky if it's not nicely sequential buried. If it's turbulent, then it's you can only see an average over a longer time. And you cannot do a high resolution like every 100 or 200 years. Then you say, well, in this 1,000-year interval where we had all this turbulent material, then the average climate was such and such. That is the information. Then you could still.
Okay. Okay. The last statement, maybe, Prof. Rink, you want to say something about this paper, this conference, and any possible thing? Prof. Rink?
Yeah. So I don't have any further things.
Right. But maybe we can consider after the pandemic, you can visit again and again our beloved country.
Yes.
You already going to Padang before?
I have never been there. No.
Never been. And that's why Mr. Hamdi Rifai would like to invite you. We so excited when you saw the lake di atas immediately and live directly.
Yeah, that would be really fantastic. Yeah. Hopefully that will be possible in the next year or two. Yeah.
I mean, we hope so.
Yeah.
And we're back on that moment coming and can't wait for that moment.
Yeah.
Thank you so much, Professor Rink. We got applause on our application, guys. You just check out your reaction, give applause over there. Thank you so much for your attention.
Thank you.
And thank you.
Welcome.
After Prof. Rink, see you when I see you again.
Bye-bye.
Bye-bye. We're going to move on to our beloved Associate Professor, Dr. Caroline. Hello, Caroline. Hi.
Hello.
Caroline.
Can you hear me properly?
Yeah.
Can you hear me?
Do I ever thinking what we already met before in another seminar?
This is the second time I participate in the ICRLP, and I am very happy to be here again.
That's okay, lovely. That I remind something like that. The girl I met before. So, would you like to teach us how we can say your name, spelling your name? I don't know. It's a French or I don't know name. What's it?
It's Bouvet de Maisonneuve. I know it's a mouthful.
Bouvet de Maisonneuve.
Yeah, Bouvet de Maisonneuve. But Caroline is fine. You can call me like that.
Okay, you already origin from France?
Yes.
All right. And here we go. Right now, you are representing Singapore.
Yep, correct.
All right. Here we go.
Singapore.
Ladies and gentlemen from Nanyang Technological University, we brought to present to you Caroline Bouvet de Maisonneuve. Wow. It's a French and just know about merci and something like that. But here we go. Check this one out. It's time to Miss Caroline.
Thank you very much. Good afternoon, everyone. Thank you for sticking around. So we're continuing with the study of our Earth system. but moving over to volcanoes. So I will present to you an updated understanding of Sumatra's volcanic eruption history. So this is a project that started 5 years ago in collaboration with Dr. Hamdi and his students. I haven't listed the full list here because it's quite long, but a big thank you to all of them for their wonderful participation in this project. So 2 years ago, when I participated in the ICRLP, we were starting this work and we were starting to make discoveries about volcanoes in Sumatra. And here I will show you how far we've gone. So to begin with, why do we even do this kind of work? So this is a map showing you all of the volcanoes in Southeast Asia with red triangles, and you can see that there are a lot. And then in addition to this, you have all of the air traffic routes, which are those black lines, which have quietened down these days with COVID, but are still pretty active. And all of the dashed lines are the sea traffic routes with boats. And you have all of the major cities. So you can see that there's a lot of human activity next to all of these volcanoes. So obviously we want to know what is the hazard for the region. So this is another map showing you, again, those volcanoes, this time with gray triangles. And in black here are the calderas. The black dots are the calderas, and those calderas produce the largest eruptions you can think of. And they're, for example, the ones that created Lake Toba, that you all know in North Sumatra. And so they can be huge, these eruptions, very catastrophic for our societies. Other examples are the eruption of Mount Krakatau in 1883 or Mount Tambora in 1815. And it's one big volcanic edifice that basically exploded over a day or two and put so much ash in the sky that in the area that it was black like nighttime for about 2 days. And then there was very big disturbance of the climate and a lot of crop failures and all widespread diseases. So we want to keep a special eye on these calderas and know how often these kinds of eruptions occur in the region. And what you can see here is that only the calderas that have a colored dot are the ones for which we know something. We know their age and we know their composition. All of the black dots, we don't know anything. So this is a compilation I did when we started the project. It was published 2 years ago. And we have updated this since. Now, we can go and study those calderas on land, okay? But it's also tricky because those deposits, then they become a soil and there's vegetation that grows on it. They can also be washed away by heavy rains during the monsoon. So all kinds of things can happen to these deposits, meaning that you might not have the full record on land. So what we have done is we have also looked at deposits in the ocean, because the ash travels far and it can rain down and fall into the oceans. So these are examples of some marine cores that have been collected during many different cruises, not by ourselves. And we have revisited those cores that are stored in different archives. So again, this is the compilation I did before we started the project. And this is what we know of the eruptive history. So we have time on the logarithmic scale here on the horizontal axis and a compositional proxy to try to have an idea of the source, where the ash is coming from. And what we can see is that we don't know of many eruptions in the past 10 to 50,000 years, okay? 10 to 75. This is the eruption of the young Toba tuff that formed the youngest eruption from Toba caldera. And so this is a very big time marker. And we see that there's 1, 2, 3, 4, 5 eruptions that we knew of. And that's about it. And then these are some older eruptions that I will not talk about in this talk. So what did we do? Well, with Hamdi and his students, we traveled from North Sumatra all the way down to South Sumatra. In many trips, we spent a lot of time in West Sumatra and Jambi. Then we had a trip to Bengkulu all the way to Bandar Lampung, and we had a couple of trips here to North Sumatra. And we visited the source regions of a number of the calderas. The other thing we did is that we revisited a number of cores. So these are two campaigns of the Sonne cruise ship, which is a German ship. And there were two campaigns for paleoclimate research. And these cores are now 10 to 12 years in age, and they're stored in Germany, in Bremen and Hanover. And we had two campaigns to Germany to subsample all of the tephra layers in these cores and date them and characterize them geochemically so that we can correlate tephra layers from one core to another and say, okay, all of these levels are part of the same eruption, or these are different eruptions. And we think it comes from this volcano or from this source region. And to date them, what we did is we took some little shells, marine shells that we call foraminifera. And they have a shell that's made of calcium carbonate. And because it's carbonate, we can date it with radiocarbon. So we took the foraminifera that are just below the ash and also sometimes just above, to be able to give the most precise age possible to the ash bed inside the marine core. So how do we do all of this? How do we go from North to South Sumatra? How do we look at more than 28 marine cores? Well, first we set up a dream team, and most of them have been through Padang. So there's Stefan, Francesca, Jeff, Marcus, Dini, Harris, Fires, and Jay, and all of them have contributed immensely to the project. Then you add on a set of wonderful local collaborators, and you go throughout Indonesia on lakes to collect some cores in peatlands, and looking at all of those caldera deposits. So thank you again to all of those students who have participated. It's been a great pleasure being with you in the field and having you in our labs and making this project happen. Then this is what some of the marine cores look like. So this is one that was collected during the Mirage cruise on which Marcus was. It's a pretty deep sea core. And so you can see that this is the background sediment in dark gray, and then these kind of tan, light brown, gray layers here. There's a little blob down here. Here there's more, is one tephra layer. And this is actually from the young Toba tuff, from Toba caldera. And we know this one is 74,000 years old. And we can highlight these tephra layers by playing with the colors of the image, the red, green, blue ratios, so we can have them come out and make sure we don't miss anything. And we can measure different kinds of proxies, such as the iron content, manganese, calcium, etc., which change where there's an ash layer. Other ash layers, these are resampled from the Sonne cruise, and these ones are more visible. Here the background sediment is brown, and you can see there's this clear salt and pepper, coarse-grained ash layer here, and a smaller ash pod up here. Here there's a thin layer here. It's actually the same as this one, but in another core, and another one up here, which is the same as this one, but in another core. Okay, and so we subsampled them, and then we study them. So how do we study, whether it's the samples from the marine cores or the samples that we collect on land? For example, this is all deposit from a caldera, and we have here Rizal, who's picking out some big pumices from this deposit. Here, this is 74 scale, and also there's a lot of pumices in here that we then study. So we can make a thin section or some kind of mount that we polish, so that then we can have a look at what those grains are. We have some crystals, like you see over here, but we also have a lot of glass, which was the liquid magma, and then it got solidified, quenched when it reached the surface. So we can look at it with an optical microscope or with a scanning electron microscope. And even to quantify the data, we then go to the electron microprobe, where we can get all of the major element composition of the glass shards of the minerals. We can also fuse the whole rock to get the whole rock composition. Now, major elements are useful, but they're not always enough to tell these different eruptions apart, because caldera-forming eruptions tend to have very similar compositions from one to the next, because they're, in a way, the most distilled magma compositions. So the most refractory elements have already been precipitated out, and you keep the lighter, the least refractory elements behind. And so what we do is we also do trace element compositions. And so these are the much less common elements, very low abundance, the ppm level, parts per million level. And we do it with a laser ablation inductively coupled mass spectrometer. So basically, inductively coupled plasma mass spectrometer. And so basically we have a laser beam, and this is the example of one glass shard. This is an image under the electron microscope. And then this is a map of a major element, calcium, done with the electron microscope. And then this is with the laser. Here we have rubidium, which is in ppm, so very small amounts, and strontium also in ppm, very small amounts. And we can analyze the composition of individual glass shards. And when they're heterogeneous, here you have little crystals, and then you can just choose some areas of glass shards that are homogeneous. So basically, we built a whole database of the compositions of all of the units we collected. And then we started pairing them together. That's how we were able to say that this deposit in the Indian Ocean comes from the same eruption as this deposit that's on land. And because of the spatial distribution on land, we can say it's from this specific caldera or volcanic center. So it's great to tie things together, but then we also need time in the whole story. You want to know when all of this happened, not just where it's coming from. And so for that, we applied a huge range of dating methods. So we applied radiocarbon dating. That's what I was telling you on the shells of foraminifera in the ocean. When we could find some charcoal in the ignimbrite deposits, we also applied radiocarbon dating. Radiocarbon dating, though, stops at about 45,000 years to 50,000 years. Whatever is older, we can't date with radiocarbon dating. So then we applied other methods, such as argon-argon dating of sanidine crystals or the ground mass of lava flows, uranium-lead dating, or uranium-thorium dating. It depends on the age. Uranium-lead is older than 300,000, and uranium-thorium is younger. And that time is of zircon crystals. Now, the problem is that uranium lead and uranium thorium, they tell you when the crystal was forming, when it was growing inside the magma. But these crystals, they can stay for a very long period of time inside the magma reservoir, hundreds of thousands of years, tens to hundreds of thousands of years. So it doesn't tell you when the eruption happened. It just tells you, okay, this is when the crystal was growing. So we need more than that. We need actually when the eruption happened. And so to make sure we have the eruption age, argon-argon works on sanidine, but most of our samples did not contain sanidine. So we were not able to apply this method. So then we went to more complicated methods using helium. So these analyses were done in Zurich. And we measured not just the uranium lead or uranium thorium, we also measured the amount of helium, which is a gas that was trapped inside the crystal. And that is a method that tells us when the eruption happened, because the helium clock starts ticking from the time of eruption and not the time of crystallization. Okay, and then I will show you the data for all of these calderas with these circles. So the little Sinkut caldera next to Mount Sinabung, the Toba caldera, I will not talk about so much because it's complicated and quite a bit is known already. Then we have the Hopong and Sipiroc nested calderas, the Maninjao caldera, which is close to you. Here, this is the region of Sungai Penuh in Jambi. And then more to the south, South Sumatra and Bandar Lampung. So starting with Sinkut, where let's travel from north to south, so you have an idea of what we have found. So this is the Sinkut caldera. This is Mount Sinabung. Medan is over here to the northeast. And basically, Mount Sinkut used to be one big volcano, like Sinabung, probably a bit bigger. And then one day it exploded, just like Krakatau in 1883 or Tambora in 1815. And from this big explosion, there's an apron of deposits to the north and an apron of deposits to the south, mapped in purple over here. And you can see these deposits are extremely thick. So this location is over here. This location is the star a bit closer. And you have for scale people in this image to the bottom, or these excavators in this image above. And so you can see there's up to 100 meters thick deposits blanketing the region around Singkut. Now, here are our ages of Singkut. The first thing to note is that over here where the star is, or this upper star near Kabanyahi, there is a place where we were able to see that the Singkut deposits are above the deposits from Toba. So that means that they have to be younger. They were deposited on top of. So the deposits from Toba had to be there before, and then the deposits are there on top. So we know it has to be younger than the young Toba Taf, which is 74,000 years. So we know it has to be younger than 74,000 years. We tried dating the zircons in there, but the zircons gave us ages of 100 all the way to 680,000 years, much, much older. So these zircons inside the deposits formed actually a long time before the caldera forming eruption happened. So these ages are interesting, but they don't tell us much about when the eruption happened. So that's why we then used the helium ages. And so these are the helium ages for each of those uranium thorium ages. We measured the helium content, and then we get a much more similar age. And those same orange dots are shown in this lower plot here where we can expand it. And they're over here, and they cluster more or less around 50,000 years. There's some large error bars, but the best mean is 51,000 years. Now we were lucky, we were able to find a piece of organic rich material. It wasn't exactly charcoal, but a very organic rich sediment that was a cluster inside the deposit. And this gave us an age of 43.7 thousand years. So in agreement with being younger than Toba, and in agreement with the helium ages within air. Okay, so together this gives us an age of about 47,000 years old on average. We also were able to analyze the composition of Singkut, and we found one layer in the Indian Ocean with the same composition. And we are also able to date it, and we got the same age here of about 44,000 years. So we now know that the Singkut caldera is 44 to 50,000 years old and is younger than the young Toba Taf. Now moving south, so we have Toba caldera that's north of this. This is the Sarula Graben, and we have the town of Sipirok over here. And there's this morphology in the landscape where we have these two nested depressions. We have an outer circle and an inner circle. And we called this inner caldera the Hopong caldera. There's a small village in the center that's called Hopong. And the outer caldera is the Sipirok caldera and the name of Sipirok town just over here. And this orange patch here is gotten from the geologic map. We visited all of these orange locations here, not this yellow star, all of the orange ones. And where it's better preserved, it looks like this welded tuff. We have Rizal for scale, looking at the outcrop. And otherwise, it's very often weathered to clay. There's a lot of geothermal activity over here. It's very hard to analyze. There is sanidine in this deposit, so we were able to get an eruption age of 584,000 years for a very old block, which we believe belongs to the outer Sipirok caldera, but we can't map it very well. And 390,000 years old for all of these other units that we attribute to the Hopong caldera. It used to be attributed to Mount Sibualbuali, but this deposit is really very large, and there's no big crater from Sibualbuali. So instead, it has to come from this Hopong caldera. Now, Maninjao, you know well, it's in your backyard or almost, a very beautiful lake. And there's the Bukit Tinggi Tuff that you can see very well in the Sianok River of Bukit Tinggi. Again, 100 meters thick in elevation. We have Stefan for scale here, and a very big unit. It had been dated before by Brent Alloway, and this is the ages they had gotten. It's this red open box. And they had combined radiocarbon and fission track eruption ages. Now, these are all of every little blue point you can see on this graph here is one zircon age using uranium thorium dating. And so you have the whole crystallization history of zircons. Zircons started crystallizing about 75,000 years ago. And they crystallize continuously all the way until eruption age. Now, people have developed a Bayesian modeling tool to try to look at, from this distribution of zircon ages, what must have been the eruption age. And so it's some probability modeling, assuming a crystallization dynamic of zircons. And it's been pretty well calibrated. And what you can see is that this is what the model predicts. It's this red shaded envelope, and it matches, it's in very good agreement with what Brent Alloway had found with other methods. And so it gives an eruption age of about 50,000 years. It confirms the previous age estimate. So a little bit older than Sinkut, but not much older than Sinkut. Now, in the region, we don't have just calderas. We have other units of interest that I will detail here. The first is Mount Malintang. So Mount Malintang is over here. It's just south of Sorik Marapi, north of Talakmau. And it turns out that although Malintang is not particularly known or studied for its volcanic activity, it's actually the source of the youngest tephra layer found in the ocean. So when you look at all of those layers in the ocean, there was already a study published in 2012. They already identified this layer. They said it was about 2,000 years old. We refined the age. It's about 1,376 years before present. So before 1960 and or 1950. And we found that the source was actually Mount Malintang. It took us a long time to visit all of the region and look at all of the outcrops and find a deposit that matches the marine composition. And here you have the marine cores in which it was found. Every little white circle is a marine core in which it was found, also this one. And this is what we call an isopac map. It tells you the outline of same thickness of the ash. It's in millimeters. So here we have 3 millimeter isopac, and here we have 1 millimeter. So within this envelope, there was at least 1 millimeter of ash everywhere. And within this envelope, there was at least 3 millimeters of ash everywhere. So quite widespread, moving to the southwest, and the youngest unit in the region. Then another interesting discovery was this double layer from Mount Tandikat. So Tandikat and Singalang are this paired volcano next to Maninjao. And Tandikat is the south summit. And there were these marine layers. And after a while, we saw these pairs. I showed you the images of those two layers inside the cores at the very beginning. They're actually from Tandikat. And so what it says is that there are two eruptions closely spaced in time, one at 4,200 years before present, and the other one at 4,600 years before present. So they're 400 years apart. And these are the isopacs again. So this is the 1 millimeter isopac. And for the youngest, and this outline is the 1 millimeter isopac for the oldest eruption. And you can see that they've traveled quite far, more westerly distribution. And those were two substantial eruptions from Mount Tandikat not so long ago. And then the other interesting volcano in the area is Mount Marapi, just to the east of Tandikat and Singalang. So we have Maninjao, then to the east we have Tandikat, Singalang, then to the east we have Marapi. And Merapi is the most active in Sumatra currently. It generally makes small eruptions. We don't really know in the historic times of any large eruptions. So volcanic explosivity index of 1 or 2. But if you look at the marine record, actually it has had several eruptions, 9.8 thousand years ago, 15, 17 and a half, 20, and then 34, 35,000 years ago. It had eruptions that were VI 4 likely. So 2 orders of magnitude bigger than what we've had now, similar to Tandikat, Singalang, or Malintang. And the deposits of these eruptions are found obviously offshore, like for Tandikat and Singalang, but some deposits are found pretty far north, more than 500 kilometers north or 500 kilometers south. So that shows you how far the ash can travel and how much can be under the ash of this one volcano during one eruption. So I think Merapi's hazard potential will have to be revised significantly, and we'll be talking with CVJHM about this because it's quite interesting. And if you look at the recurrence times, it's every 2.5 to 5, but there can be longer breaks in time, okay? So 9,000 years old might sound old to us, but if you see that here there was 14,000 years with no eruption, well, it doesn't mean, it means that there could still be other eruptions from Merapi that are big in the future. Now moving a bit south in Diatas, this is Lake Diatas that Rink was talking to us about earlier. Well, Lake Diatas also has an old caldera-forming eruption, maybe from Lake Diatas, maybe from somewhere else. We don't know where the source is. But this is the Diatas tuff. It's quite weathered, and it's been dated both by Argon and with the Zircon ages at about 400,000 years. And in the peatlands of Diatas, there are some younger glass shards. We were not able to constrain the age. It has to be older than 11,000 years old. And they are most likely from Mount Talang. So we have evidence for 2 large eruptions from Mount Talang, but we don't have good constraints on the age. Then this is the town of Sungai Penuh over here. We're in the Jambi region. We have Lake Kerinci, where we did some geophysics and we saw it was a caldera. And we have deposits from what we believe is from this caldera, which is this ignimbrite in gray to the right that we call the Sungai Penuh tuff. Then south of it, there's this big depression where the town of Lempur is situated, and we call it the Lempur caldera. And so we have the tuff from the Lempur caldera that we mapped in red over here. There is this sequence of pyroclastics deposit that we call the Kotopetai tuff. That's on the northern rim of the caldera of Lake Kerinci. And we have these blue stars that contain ashfall deposit that we call the Jujun pyroclastics. And we were able to date these 3 calderas, the Sungai Penuh tuff, the Lempur tuff, and the Kotopetai tuff at 290, 215, and 148,000 years. This is approximate. I didn't put the error bars because we're still fine-tuning a lot of these ages. It's very model dependent, but it's on this order. And for the Jujun tephra, it's been correlated with a layer in the Indian Ocean. So we know it's 41,000 years old from this layer in the Indian Ocean. And what is the source? We postulate it might be Mount Kunyit because of the distribution of the ash, and the position in the Indian Ocean could also be Mount Raya. We're not sure. Now more to the south, this is Mount Dempo. So over here we're in South Sumatra, not very far from Bengkulu. And we have this Pazoma tuff, which is a very welded ignimbrite that's confined to the river valleys over here. We got a zircon age of 430,000 years. It's very welded, and we're not sure about the source. There's no crater or caldera. There's only this kind of weird elliptical shape over here. Could it be a source region? We don't really know. And it was also recognized in some distal marine cores. So it probably was a substantial eruption at the time, putting a lot of ash in the Indian Ocean too. Now this is Lake Ranau and the caldera of Ranau. It had been dated previously by radiocarbon, and this is the age over here at 36 to 37,000 years old. Again, when you date the zircons, we get very old ages, more than 100,000 years old, which don't reflect the true age of eruption, but rather the age of crystallization. And when we apply the helium dating, we get this spread, which is large, but surrounds the radiocarbon age, and therefore confirms the age of about 36,000 years old. What's interesting is that the Ranau deposit is very, very prominent in the marine record. So we found it in at least 5 different cores, and it traveled, the ash from this Ranau caldera traveled all the way to North Sumatra. And you can see here that there are different spatial distribution patterns of the ash, sometimes going north, sometimes going south, sometimes going west, and this reflects the time of the year when those eruptions happened. So in the future, more work could be done looking at atmospheric circulation patterns to understand when those eruptions happened and what were the implications maybe on the climate. And this is, you see how well we can correlate the different layers with each other inside the different cores. They're really, really spot on. And this is the spatial footprint of the Ranau caldera. And because it's so widely spread, if we know the age very well, then this is a time marker through all of the cores. So then we can date cores now by identifying Ranau and saying, okay, this is 37,000 years old. Now, if we go to Bandar Lampung, there's a depression south of Bandar Lampung inside the Lampung Bay. Could it be a caldera? No one really knows. More work would need to be done. There are these tuffs all around. We studied this location here at the ITERA campus, and this caldera, this deposit is 1.2 million years old. So quite old actually, but the South Sumatra climate is drier than the northern part, and so deposits are generally better preserved. And here there are some cliffs near the bay of welded tuff, and we were wondering whether it was the same caldera, but no, the composition is different, and this age is much older. It's 6.2 million years old. So this is a pretty old deposit. Now, what is the source exactly we're hypothesizing? Mount Rajabasa was proposed, but it doesn't have any big craters, so it's probably not a good candidate.
We got 5 minutes.
Now to
more?
finish, yeah, I'm done. To finish, we have
right,
Krakatau in the Straits, and it was found. So we have the 1883 eruption that we recognize in the cores, and this is the spread of ash from Mount Krakatau, and we have evidence for 3 older eruptions, probably significant in size, before the 1883 eruption. So we've been putting all of these tephra layers together. This is an example from a subset of our cores. It's obviously a lot of work tying and pairing those little layers together and with a source region. And what we have for now is that we have at least 25 large-scale eruptions, VEI4 or larger. VEI4, for example, is Mount Kilut in 2014. This is a VEI4 eruption in the past 75,000 years. But there are older eruptions too that are large, just like Toba, and that are older in age. So putting the whole story together, this is all of the ages of the calderas that I've presented you. And you can see that we've increased the number of known and studied calderas from 7 to 15. And we've increased the number of Plinian VEI4 eruptions from 8 to 49. So this is a significant increase in the number of eruptions from Sumatra that were previously known. You can see that North Sumatra is rather quiet, West Sumatra is the most active part of Sumatra, and South Sumatra is intermediate. We obviously characterize all of the geochemistry. I didn't show all of this, but there are a lot of trends, and each eruption has its specificity. But what is interesting is that we have some variations between North Sumatra, West Sumatra, and South Sumatra in the composition. So the frequency of eruption is low here, very high here, and intermediate there. The potassium content is high here, very low here and intermediate here. And this matches some variations in tectonic trends, but actually quite few of them. And what it matches the best is the earthquake frequency. We have a high earthquake frequency in the north and intermediate to high in the south, and the lowest earthquake frequency in central part. And this is due, we believe, to the subduction of fracture zones. So we have a lot of fracture zones being subducted here beneath North Sumatra, which drives high earthquake frequency, high potassium content, and probably more magma accumulation inside the crust. Fewer eruptions, but larger in size. Whereas in this central part here, no fracture zones are being subducted. So it's drier. We have more eruptions, but of smaller sizes. And then when we go back to the south, it's intermediate in all of those. So the overall structure of the subduction zone has a very significant control on the eruption frequency and magnitude and composition. And that is it. Thank you for your time.
Thank you, Caroline. We got, yes. If you have any question, guys, you just check out your chat room and then write down your questions. So that's gonna be Caroline gonna be answered. And as you know, if you from Padang, Indonesia, it's a lot name and the title Lake Mount. We are so familiar with the Caroline presenting before. And then it seems like we're around of the Sumatra, which is like going to this place until next place and the next place. All right. If anybody have any question for the last moment, maybe Mr. Hamdi, you want to check out to Caroline?
Hamdi knows my work.
I'm very excited with your result. very excited. So, how big's our work before, and then I know how. Yeah, I think it's amazing. So, in conclusion, we can see the eruption from the young to the older, right? Younger to the older, and is it the sample that we collect before all?
Yes. So what we did is we combine all the type of sample to put, because we have all of the deposits that we saw together, the outcrops, where we go and we collect the pumices from the side of the roads and from the quarries. Then we also have, when we did the peat coring, we also did all of the separation to get the glass shards out of the peat. We didn't find any nice layers in the peat, but when you do the separation, we find some glass shards, and it still helps you to say where some of the eruptions is coming from. And then we also went to Germany to get these marine core samples to complement the story. So what I present is all of the data together. We're still fine-tuning a lot of things, but little by little we're getting there.
All right. I think if Ring collaborating with us and then combine that data, then we know what happened with climate change while the eruption happened. I think it's very interesting.
Yes, it is. I agree. And I think once we know what happened when, we will also have the spatial pattern, as I was telling you. So sometimes, for example, Ranau follows the outline of Sumatra, goes along the coast, but Tandikat goes out to the west completely. And I think it's not going to have the same impact on people in the cities, but also not the same impact on climate. So when we have a better understanding of all of those, then we can then start doing more work with people like Rink or other researchers to look at the interaction between the volcanoes and the climate.
Yes, of course. Yeah. You still have ring here?
Yeah.
No, I think
Ring's
he had
gone?
to leave.
Was gone?
Yes, unfortunately, he says he had to leave.
Yeah. Thank you, Caroline. And we hope more the
Yes.
bigger result about that. And we got we will get many information about the volcanic activity, especially in Sumatra. And maybe next in future we will go to other place in Sumatra again. Yeah, I hope so. Yeah, thank you, Caroline. Yeah.
Thank you. Thank you
Yeah.
for inviting me to ICRLP and for giving me the time to share this, and more collaborations in the future.
Yeah.
All right, that's good.
And send my regard to your family in France, right? When you come back to Singapore?
January.
January. Oh, so long.
Yeah.
Okay.
This is not just like a question and answer portion or question and answer part, but just like we saw that mini reunion between our beloved Mr. Hamdi and our Miss Caroline. And we hope we have and that the part. Maybe sometime if Mr. Hamdi goes to Singapore or somewhere, yeah, we can together, right? And
we
then
bring,
Caroline,
you should follow with us.
All right, Caroline, because you are the last keynote speaker for today, and absolutely, we're moving on to our Miss Sapriani. Miss Nini, are you there? Miss Nini? I believe Miss Nini have one question, or because she was already study from Japan, and of course, same with Mr. Hamdi. Mr. Nini, are you there? Mr. Nini not really connected with us, but that's okay. Miss Caroline, you want to say something at the Indian or like a close statement?
Just the last thank you. Thank you for organizing and thank you for the collaboration.
Yeah.
And we thanks to you.
You are welcome.
Thank you.
And
thank you. Wow.
Coffee.
All right. Let's cheers together. Cheers together. All right. Thank you so much. Merci.
Miss
Caroline. Thank you.
Di atas.
Yeah, oh, nice.
Thank you so much. Let's give an applause for reaction to Miss Caroline, ladies and gentlemen, guys. You can use your reaction. Thank you so much. And see you when I see you again. All right, that's it for today. Is it last part on the keynote speaker? Oh my gosh, Alhamdulillah. All right, ladies and gentlemen, today is a big day and we already start in the morning until right now in the afternoon. And we're going to move on to tomorrow in the morning, which is like 7 or 7:30. Anybody? Give me advice, 7 or 7:30? General Chair, Mr. Riri? Miss Riri, which one we start tomorrow, our international event for the next keynote speaker, 7 p.m. or 7:30, or same time with that, the part in the morning, which is like 8 a.m. Okay, 8 a.m. in the morning. All right, don't forget to click the link on the chat room for your attendance. I'm gonna do copy again. Oh, sorry. So many laptop and PC over here, so I can't. Don't forget to click below and then write down that the attendance link on this session. And then it's time for the end of this moment. See you again for tomorrow morning at 8 a.m. in the morning. And any comment? Paralysis? Yes, after this, gonna be paralysis. Right now, Team IT gonna be making you go to paralysis, but for the keynote speaker, it's the end, and see you again tomorrow with the keynote speaker. Team IT, would you like to help us to show breakout rooms on the app? That's it, what I mean. Yes, we got 109 participants. Would you like to join which one the room you want to join? We got you just like 1 until the 10 rooms. you just click which part and which room you want to go there. All right. As based on the data, room 1 until room 3, it's talking about the scientific and sciences of the physics, and 4 until the 10, it's talk about educational of the physics. Yes, that's what I meant. We still got, wait a minute, 91, 91 participants not really join it. Would you like click below on your breakout rooms, and don't forget to take a look your attendance in afternoon season. We still got 75. Silakan dipilih mau di room berapa. Tadi sudah disampaikan roomnya 1 sampai 10, 1 sampai 3 adalah room untuk yang pembahasan mengenai atau minat mengenai fisika murni atau ilmu fisika. And then room number 4 until number 10, it's talking about the education atau berhubungan dengan kependidikan. Yes. Ya, kita cek dulu. We gotta check out the room number 10. Still need a lot of participants. Room number 9, just 1% room joined. Room number 4, it just 1. Number 6, just 1% joined up. Room 7, just 1. And room number 9, just 1 also. We still got a waiting room. It's a 30. Oh, wait a minute. All right, here we go. All right, see you guys. Enjoy your topic on that room.
mengusik jiwa ini. Ku harap sayang kau tabah menghadapi.
Beli jajanan di GoFood pakai GoPay bisa dapat diskon.
Haruskah berakhir sampai di sini? Cinta yang dulu kita bina kini telah layu di dalam hati. Sudahlah, cukuplah sampai di sini. Percuma saja berkasih, kita sudah
Lagu baru kan?
sehaluan lagi. Perbezaan kasta yang jauh, aku tahu siapa diriku.
directornya
berakhir di sini
boleh
saja.
pilih playlist lain gitu, atau malam atau apa. Makasih Evan. We love you.
pasro haki Ido hatabi tua na ujui Tangi aku maa Tumdi dia pea Ula hodoi aholongan Tata bulani Gora horoku magoanmu Hataho mahoromi Tunda sorupa Molonda wansiaku Totong nobo adi Nami adi bagas rohanko Torang pei Sinori atogi Naro manggodaan Alai rohakan Jangan lupa Tuhan Bos mari Tuhan wasiatku Dan namu barohati Dan namu barohati Tuhan Barosor rohani Angin aku marah Tinggi dia biar Tubuhlah hutui haholungan Tatap bulan Manggo satu kipe Romansa insan pemimpian Di masa iko bisa pusiai Nacido di Baekom Sinari yang mulai pasidikona Molo hutene poko Di malam minggu Lagu dengan alasan Si mata di doko tua wiko Step up, jaga-jaga kasihan Dengan kamu pikir Lasto nang roh aku Asal mana tahu Tapi sobat akan kihui dawa Makan rencana kodok tak asingi Di ida mata kiri Soi nama desmana Di jantan kabei Dirian sadisian Ambai nampong Sangguni ngobukno Barhusor di horong Natu magon nama Sirang siapo Darah di bang Darah Tuhan siang Romansa insan pemimpian Di masa iko bisa pusiai Nacido di Baekom Sinari yang mulai pasidikona Molo hutene poko Di malam minggu Lagu dengan alasan Si mata di doko tua wiko Step up, jaga-jaga kasihan Dengan kamu pikir Lasto nang roh aku Asal mana tahu Tapi sobat akan kihui dawa Makan rencana kodok tak asingi Di ida mata kiri Soi nama desmana Di jantan kabei Dirian sadisian Ambai nampong Sangguni ngobukno Barhusor di horong Natu magon nama Sirang siapo Darah di bang Darah Tuhan siang Dirian sadisian Ambai nampong Sangguni ngobukno Barhusor di horong Natu magon nama Sirang siapo Darah di bang Darah Tuhan siang I got bands, I got bands, I got गाड़ी इंडेवर छोरी गेवर वर्गी साइड में पापा का लाडला सो मम्मी का पराइड में गाड़ी इंडेवर छोरी गेवर वर्गी साइड में रे पापा का लाडला सो मम्मी का पराइड में डाटे तभी डटे कोन्या एर करी तजी पटे कोन्या.
Ya, kembali lagi di Judika Studio kali ini. Saya bersama abang dan adik saya, ada Bang Erik dan juga adik saya Tiro Syotang akan bawakan sebuah lagu ciptaan Bang Erik Syotang. Ini lagu lama saya bersama saudara-saudara kandung saya yang tergabung dalam Sisol Hot.
Urang basiang pagi rumpui salai indah urang sisokan dulu setengah mati cinto denai harokan batarimo pilihan urang tua ibu hati di dado ino di caraco adia biarkan denai manangguang surang
Apa dia benar rupanya mencari dendam kenangan cinta kita barasuai ada harapan angkanya denai kembali pulang
usah diingat di kana jua membuai luka badara ulang di hati denai lah mulai lupa usahlah dia datang bayi jua.
Maafkanlah denai maafkanlah sayang terima maaf denai oi udah
Bukan nutani oh denai manarimo tapi hati latalan juta luko. sudah urang basiang padi rumpui salai indah urang sisokan dulu satengah mati cinta denai harokan batarimo pilihan urang tua ibu hati di dado ihino di caraco adia biarkan denai mananggung surang
Papa dia benar udah rupanya mencari dan kenangan cinta kita barasuai ada harapan makanya dengan kembali pulang
Usadi ingin dikana jua membuai luka badara ulang di hati denai lah mulai lupa usala adia datang bayi
maafkanlah denai maafkanlah sayang tadi bangga maaf denai oi udah
bukan nyutani oh denai manari mau tapi hati latalan jota luko
ಸೆಲ್ಲಲ್ಲಿ ಯಾರಿದ್ದಾರೆ?
ಕರ್ಪುಕಾಗೆ ಸರ್.
ಡ್ಯೂಟಿ ಮೇಲೆ ಯಾವ ಕಳ್ಳ ಇದ್ದಾನೆ?
ಮಲ್ಯ ಸರ್, ವಿನಯ್ ಮಲ್ಯ.
ಸರ್ ಇದೊಂದ್ಸಲ ಬಿಟ್ಬಿಡಿ ಸರ್.
ನಮ್ಮ ಅಜ್ಜಿ ಕಾಲಕ್ಕೆ ಬೆಳ್ಳಿ ಉಡ್ದಾರ ಅದನ್ನು ಬಿಟ್ಟಿಲ್ವಲ್ರಿ?
ಕಳ್ತನದ ಕೆಲ್ಸ
berakhir sudah impian cinta tinggallah puing-puingnya mimpi yang indah tak jadi nyata terkikis ombak menerpa
aku yang dulu engkau sayangi mengapa kau tinggal pergi oh di manakah janji yang suci yang katamu tak berbagi
ku ingin kau mengerti apa yang ku alami takdir diriku harus melangkah jauh juo samo disambui jo hati suko
Batangan tumbuh di tanah lereng tionan jatuh ke para urang
jadi awal orang ketujuh masih dekat kita dahulu
Panen di awal kayu di urang masuk di kita bila kasana
selagi masih berusaha Tuhan nan indah kasih-sia
Indah kalari kunduan di kaca
indah karya lawi di timur
mencari kita coba doa
nan rasa kita datang jua
Entah bila kelari buah masa di ujung ranting terasa tinggi jua
lamo jo lambe kajatuah juo samo disambui jo hati suko
Batangan tumbuh di tanah lereng tionan jatuh ke para urang
jadi awal orang ketujuh masih dekat kita dahulu
Panen di awal kayu di urang masuk di kita bila kasana
selagi masih berusaha Tuhan nan indah kasih-sia
Indah kalari kunduan di kaca
indah karya lawi di timur
mencari kita coba doa
nan rasa kita datang jua
레벨업 할 준비됐어? 나 진짜 높지? 내가 더 높을걸?
여기서
보스가 바보인다고!
우린 지금도
올라가는 중!
올라가는 중
얘들아, 다 올라갔으면 지구 밑으로 와.
레벨업! 어리드 모브 코리아!
Aku ngebon pintar
Gak jadi pemain basket kayak kakak.
Jagoan mama, jadi apa aja bisa. Asal daya tahan tubuh kuat. Aku pilih Hilo School untuknya. Tinggi kalsium dan tinggi vitamin D.
Jadi pemain basket bisa.
Hilo School, tumbuh tuh ke atas.
Lai dan naik kapulang, basabalah dia menanti di ranah minang. Usah ada ragu jo bimbang, genggamlah taguh janji nan kita karang.
Allah bertahun udah dirantau, dinai menanti, do hati risau, dinai merindu, candu kehilangan. Dinai merindu, candu kehilangan.
Buang perasaan konan di hati, picayolah dia picayo jo janji cinta. Udah indah kamu ke janji, indah kamu menduakan cinta adianan suci.